In 1901, a group of Greek sponge divers, working off the coast of the tiny island of Antikythera, midway between Crete and the Greek mainland, discovered the wreck of an ancient Roman cargo ship lying on the seafloor at a depth of approximately 45 meters. The wreck contained the usual cargo of a wealthy Roman vessel: bronze and marble statues, pottery, glassware, jewelry, and coins. But among the corroded bronze and the encrusted artifacts, the divers recovered something that did not fit, something that would take nearly a century to understand, something that would force historians to rewrite the history of human technology. It was a lump of corroded bronze and wood, roughly the size of a shoebox, encrusted with marine deposits and fused into a single mass by 2,000 years of immersion in salt water. When it was first recovered, no one knew what it was. The archaeologists who examined the wreck were far more interested in the statues and the other art objects, which were immediately recognizable as masterpieces of ancient Greek and Roman sculpture. The corroded lump of bronze was set aside, catalogued, and largely forgotten. Then in 1902, the archaeologist Valerios Stais noticed something that changed everything. As the marine encrustations were carefully removed from the bronze mass, Stais saw what appeared to be gear wheels, precision-cut, interlocking gear wheels, with teeth of extraordinary fineness and regularity, embedded in a mechanism of such complexity that it would not be matched in the historical record for over 1,000 years. Stais realized that he was looking at a machine, a device of some kind that used interlocking gears to perform calculations or to model physical phenomena. He was looking at a computer, built 2,000 years ago, in an age when such technology was not supposed to exist. The device that Stais had identified is now known as the Antikythera mechanism, and it is by a considerable margin the most extraordinary artifact ever recovered from the ancient world. It is an analog computer, a mechanical device that used a system of at least 30 interlocking bronze gears to model the movements of the sun, the moon, and the planets through the sky, to predict eclipses, to track the cycles of the ancient Greek calendar, and to calculate the dates of the ancient Olympic Games. It is a device of such sophistication, such precision, and such conceptual ambition that its discovery has fundamentally altered our understanding of what the ancient Greeks were capable of building and what they understood about the mechanics of the cosmos. By the end of tonight, you are going to understand what the Antikythera mechanism is, how it worked, who might have built it, and what its existence tells us about the state of ancient Greek technology, science, and engineering. You are going to learn about the decades of painstaking research that have been required to decode the device, the specific scientists and scholars who have contributed to that decoding, and the specific discoveries that have emerged from the most advanced imaging technologies of the 21st century. You are going to see how the Antikythera mechanism is not merely a curiosity or an anomaly, but a window into a lost world of technological capabilities that was far more advanced than anything we previously imagined. And you are going to confront a question that the mechanism forces us to ask. If the ancient Greeks could build this, what else could they build that we have not yet found? Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The Antikythera mechanism sat on the floor of the Mediterranean Sea for approximately 2,000 years. When it was recovered, it was so badly corroded that its true nature was not recognized for decades. And when it was finally understood, it rewrote the history of technology, revealing that the ancient world possessed capabilities that we had assumed were invented over a millennium later. A computer, built before the fall of the Roman Republic, designed with a precision that would not be achieved again until the clocks of medieval Europe. That is the story we are about to tell. Now let us begin. The implications of the discovery extend far beyond the history of a single device. The Antikythera mechanism challenges the fundamental assumptions that historians have held about the trajectory of technological development in human civilization. It reveals that the boundary between ancient and modern technology is not as clear as we have been taught to believe. It suggests that the ancient world possessed capabilities that were systematically lost during the decline and fall of the civilizations that developed them, capabilities that had to be rediscovered independently centuries or millennia later. And it raises the haunting question of what other technologies might have existed in the ancient world that have left no trace in the archaeological or the literary record, technologies that were built, used, and destroyed without ever being found. The mechanism is often described as the world's first known analog computer. But that description, while accurate, understates its significance. It is not merely the first known computer. It is evidence of an entire tradition of precision mechanical engineering that existed in the ancient world and that was lost, a tradition whose full scope and whose full achievements are unknown to us, because the Antikythera mechanism is the only surviving physical example. The device is not an anomaly. It is a window into a world of technological capability that we are only beginning to understand. The questions that the mechanism raises are not merely academic. They touch on fundamental assumptions about the nature of human progress, the permanence of technological achievement, and the limits of what the historical record can tell us about civilizations that existed before our own. If the ancient Greeks could build a device that predicted eclipses, tracked planetary positions, and calculated the dates of the Olympic Games, what else could they do that we have lost all evidence of? What other traditions of ingenuity existed in the ancient world that have left no physical trace? And what does the survival of this single corroded device tell us about the relationship between what survives and what is lost, between what we know and what we have forgotten? To understand the significance of the Antikythera mechanism, we must first understand the world that produced it. And that means we must understand the state of Greek science, mathematics, and technology in the centuries before the Common Era, a state of knowledge that was far more advanced than most people realize, and that provides the intellectual context within which the mechanism was conceived and constructed. The ancient Greeks were, by any measure, among the most intellectually accomplished people in the history of civilization. In a span of approximately 5 centuries, from roughly the 6th century before the Common Era to the 1st century before the Common Era, Greek thinkers made fundamental contributions to mathematics, astronomy, physics, philosophy, medicine, engineering, and virtually every other field of intellectual inquiry. The scope and the depth of these contributions are so extraordinary that they continue to form the foundation of many modern disciplines, and the names of the Greek thinkers who produced them, Euclid, Archimedes, Aristotle, Plato, Hippocrates, Ptolemy, Eratosthenes, Aristarchus, are among the most famous in the history of human thought. The mathematical achievements of the ancient Greeks were particularly relevant to the construction of the Antikythera mechanism. Greek mathematicians developed the rigorous system of proof-based reasoning that remains the foundation of modern mathematics. Euclid's Elements, composed in the 3rd century before the Common Era, established the axiomatic method that is still used in mathematical reasoning today. Archimedes, who is widely regarded as the greatest mathematician of the ancient world, made contributions to geometry, calculus, and mechanics that were not surpassed until the scientific revolution of the 17th century. The mathematical sophistication of the Greek tradition was essential for the design and the construction of the Antikythera mechanism because the device's gear ratios embody precise mathematical relationships that model the astronomical cycles of the sun, the moon, and the planets. The astronomical knowledge of the ancient Greeks was similarly advanced. Greek astronomers had been observing and recording the movements of the celestial bodies for centuries, and they had developed sophisticated models to explain the patterns they observed. Hipparchus, who worked in the 2nd century before the Common Era and who is often regarded as the greatest observational astronomer of the ancient world, compiled a catalogue of approximately 850 stars, measured the length of the solar year to within 6.5 minutes of the modern value, discovered the precession of the equinoxes, the slow wobble of the Earth's axis that causes the positions of the stars to shift gradually over time, and developed the mathematical techniques of trigonometry that were essential for astronomical calculation. The astronomical knowledge encoded in the Antikythera mechanism reflects the work of Hipparchus and his predecessors. The mechanism's gear ratios embody specific astronomical periods that were known to the Greek astronomers, including the Metonic cycle, the 19-year period after which the phases of the moon repeat on the same dates of the solar calendar, the Callippic cycle, which is 4 Metonic cycles minus 1 day, and the Saros cycle, the 18-year period, at which the pattern of solar and lunar eclipses repeats. These cycles had been discovered through centuries of careful astronomical observation, and their incorporation into the mechanisms demonstrates that the device's builders possessed a comprehensive understanding of the mathematical relationships that govern the movements of the sun, the moon. The engineering tradition of the ancient Greeks provides the practical context for the construction of the mechanism. The Greeks were skilled metalworkers, capable of casting, forging, and machining bronze and other metals with a precision that is evident in the surviving artifacts of Greek craftsmanship. The technique of gear cutting, which was essential for the construction of the mechanism, was known in the ancient world, though evidence for its use before the Antikythera mechanism is limited. The fact that the mechanism's gears are cut with a precision and a regularity that implies the use of specialized tools and techniques suggests that the builder or the builders of the mechanism had access to a well-developed tradition of precision metalworking. The figure of Archimedes, who lived and worked in Syracuse in the 3rd century before the Common Era, is particularly relevant to the story of the Antikythera mechanism because ancient sources describe him as having built mechanical devices that modeled the movements of the celestial bodies. The Roman orator Cicero, writing in the 1st century before the Common Era, described 2 such devices that had been built by Archimedes and that had been brought to Rome after the Roman conquest of Syracuse in 212 before the Common Era. One of these devices, according to Cicero, was a sphere that showed the movements of the sun, the moon, and the 5 known planets, and that could predict eclipses. The description sounds strikingly similar to the Antikythera mechanism, and it suggests that the mechanism may have been part of a tradition of mechanical astronomical modelling that was associated with the school of Archimedes. The connection between the Antikythera mechanisms and the Archimedean tradition is strengthened by the geographical evidence. The shipwreck in which the mechanism was found was located on a trade route that connected the eastern Mediterranean, including the Greek islands and the coast of Asia Minor, with Rome and the western Mediterranean. The ship's cargo, which included luxury goods and works of art, suggests that it was carrying the possessions of a wealthy Roman who was transporting Greek cultural treasures to Rome, a common practice in the late Roman Republic, when Roman conquerors and collectors systematically looted the artistic and intellectual treasures of the Greek world. The mechanism may have been among these looted treasures, a product of the Greek engineering tradition that was being transported to Rome for the entertainment or the instruction of its new Roman owner. The dating of the mechanism has been the subject of extensive scholarly investigation. The coins and the pottery found in the shipwreck suggest that the ship sank in approximately 70 to 60 before the Common Era. The astronomical calculations encoded in the mechanism, however, appear to be calibrated to an earlier date, possibly around 150 to 100 before the Common Era, suggesting that the mechanism was built several decades before the ship that carried it sank. This discrepancy suggests that the mechanism was already an antique when it was loaded onto the ship, a valued object that had been preserved for decades before being lost in the shipwreck. The cultural context of the mechanism's creation is the Hellenistic world, the civilization that was created by the conquests of Alexander the Great, and that flourished across the eastern Mediterranean from the late 4th century to the 1st century before the Common Era. The Hellenistic period was an age of extraordinary intellectual and technological achievement, during which the scientific and mathematical traditions of classical Greece were extended, refined, and applied to practical problems in ways that had not been attempted before. The great centers of Hellenistic learning, including Alexandria in Egypt, Pergamum in Asia Minor, and the island of Rhodes, were the most advanced scientific and technological institutions in the ancient world, and they produced innovations in astronomy, mathematics, engineering, and medicine that represented the peak of ancient intellectual achievement. The island of Rhodes, which was a major center of astronomical research in the Hellenistic period, has been suggested by several scholars as the most likely place of origin for the Antikythera mechanism. The astronomer Hipparchus, whose astronomical data is encoded in the mechanism, is known to have worked on Rhodes, and the island was home to a tradition of astronomical instrument making that could plausibly have produced a device of the mechanism's sophistication. The philosopher and astronomer Posidonius, who established a school on Rhodes in the 1st century before the Common Era, is also known to have built mechanical devices that modelled the movements of the celestial bodies, and he has been suggested as a possible builder or commissioner of the mechanism. The scientific tradition that produced the Antikythera mechanism was not operating in isolation. It was part of a broader intellectual culture that valued the pursuit of knowledge for its own sake and that invested substantial resources in the support of scientific research. The Ptolemaic dynasty that ruled Egypt from the death of Alexander the Great until the Roman conquest maintained the Library of Alexandria and the associated research institution known as the Maution, which provided scholars with the financial support, the research facilities, and the intellectual community that were necessary for sustained scientific inquiry. The kings of Pergamum maintained a similar library and research institution in their capital. These institutions created an environment in which scientific research could flourish, and they produced the intellectual achievements that made the construction of the Antikythera mechanism possible. The relationship between the Antikythera mechanism and the broader history of computing is one of the most fascinating aspects of the device's significance. The mechanism is not merely an astronomical instrument. It is a computing device, a machine that uses mechanical components to perform calculations that would otherwise require extensive mathematical computation. The gears of the mechanism are the physical embodiments of mathematical equations, and the device as a whole is a mechanical instantiation of a mathematical model of the cosmos. In this sense, the Antikythera mechanism is a computer in the most fundamental sense of the word, a machine that computes, and its existence 2,000 years ago challenges our assumptions about the history of computing and about the technological capabilities of the ancient world. The broader context of Hellenistic technology provides essential background for understanding the mechanical tradition that produced the Antikythera mechanism. The Hellenistic period, roughly the 3 centuries between the death of Alexander the Great in 323 before the Common Era and the Roman conquest of Egypt in 30 before the Common Era, was one of the most technologically creative periods in human history. During this period, Greek engineers and inventors developed a remarkable range of mechanical devices, including water-driven automata, pneumatic devices, precision instruments for surveying and astronomy, and sophisticated military engines that were used in the defense and the siege of cities. The work of Hero of Alexandria, who is believed to have lived in the 1st century of the Common Era, provides extensive evidence for the mechanical tradition of the Hellenistic period. Hero wrote detailed treatises on pneumatics, mechanics, and automata that describe a wide range of mechanical devices, including steam-driven devices, coin-operated machines, automatic doors, and theatrical devices that used complex systems of pulleys, gears, and pneumatic tubes to produce dramatic effects. While many of Hero's devices were intended for entertainment rather than for practical use, they demonstrate a level of mechanical sophistication and a command of engineering principles that are consistent with the tradition that produced the Antikythera mechanism. The work of Ctesibius of Alexandria, who lived in the 3rd century before the Common Era, provides additional evidence for the Hellenistic mechanical tradition. Ctesibius is credited with the invention of the water clock, the force pump, and the hydraulic organ, devices that use the principles of pneumatics and hydraulics to perform useful work. Ctesibius's inventions demonstrate a sophisticated understanding of the properties of fluids and gases that was far in advance of anything in the European tradition until the modern era and they suggest that the Hellenistic engineers possessed a body of theoretical and practical knowledge about the behavior of physical systems that informed their mechanical work. The tradition of astronomical instrument making in the Hellenistic world provides the most direct context for the construction of the Antikythera mechanism. The astronomical instruments that were used by Hellenistic astronomers, including the armillary sphere, the dioptra, and the astrolabe, were precision-manufactured devices that required careful calibration and that embodied specific mathematical relationships in their physical design. The construction of these instruments required the same combination of mathematical knowledge and mechanical skill that was required for the construction of the Antikythera mechanism, and the tradition of astronomical instrument making provides a plausible institutional context within which the mechanism could have been designed and built. The institutional infrastructure that supported Hellenistic science and technology was one of the most important factors in the development of the mechanical tradition. The Moution of Alexandria, which was established by the Ptolemaic dynasty in the early 3rd century before the Common Era, was the most important research institution in the ancient world, providing scholars and engineers with the financial support, the research facilities, and the intellectual community that were necessary for sustained scientific and technical work. The Moution housed the famous Library of Alexandria, which was the largest collection of books in the ancient world, and which provided access to the accumulated knowledge of the Greek, Egyptian, Babylonian, and Persian intellectual traditions. The Babylonian astronomical tradition, which had been developing for over a millennium before the Hellenistic period, was an important source of data and methods for the Greek astronomers who designed the Antikythera mechanism. The Babylonian astronomers had compiled extensive records of astronomical observations, including the positions and the movements of the sun, the moon, the planets, and the stars, over a period of many centuries. These records, which were transmitted to the Greek world through channels that are not fully understood, provided the empirical foundation on which the Greek astronomical models were built. The astronomical cycles that are encoded in the Antikythera mechanism, including the Metonic cycle, the Saros cycle, and the planetary periods, were originally discovered by the Babylonian astronomers and were subsequently refined and mathematized by the Greek astronomers who designed the mechanism. The role of patronage in the development of Hellenistic technology deserves emphasis. The construction of a device as complex as the Antikythera mechanism would have required a significant investment of time, materials, and skilled labor, and it is unlikely that such a device could have been built without the financial support of a wealthy patron. The Hellenistic kings, who were enthusiastic supporters of science and technology, are the most likely candidates for the patronage that funded the construction of the mechanism. The Ptolemaic kings of Egypt, the Attalid kings of Pergamum, and the rulers of the island of Rhodes are all known to have patronized scientific research and the construction of precision instruments, and any of them could plausibly have commissioned the construction of a device like the Antikythera mechanism. The specific astronomical knowledge that is encoded in the Antikythera mechanism is worth examining in more detail because it provides evidence for the state of astronomical understanding in the Hellenistic world. The mechanism's solar display tracks the position of the sun against the zodiac throughout the year, showing the sun's apparent motion along the ecliptic, the path that the sun appears to follow across the sky over the course of a year. The solar display uses a simple gear train that converts the rotation of the input shaft into the steady motion of the sun pointer, with the gear ratio calibrated to match the length of the tropical year. The lunar display is considerably more complex because the moon's motion is not uniform. The moon moves faster when it is closer to the Earth and slower when it is farther away, a consequence of the elliptical shape of its orbit. The Antikythera mechanism models this variation in the moon's speed using the pin and slot mechanism that we described earlier, which converts the uniform rotation of one gear into the varying rotation of another. The gear ratio of the lunar train is calibrated to match the length of the sidereal month, the time it takes for the moon to return to the same position relative to the stars, and the pin and slot mechanism superimposes the variation in the moon's speed that is caused by the eccentricity of its orbit. The eclipse prediction function of the mechanism is one of its most impressive features. The mechanism's back dials include a display that predicts the dates on which solar and lunar eclipses will occur, using the Saros cycle, the 18-year period after which the pattern of eclipses repeats. The Saros cycle was discovered by the Babylonian astronomers and was adopted by the Greek astronomers as the basis for their eclipse prediction methods. The mechanism's eclipse display shows the months in which eclipses are predicted to occur, along with inscriptions that describe the characteristics of each predicted eclipse, including whether it is a solar or a lunar eclipse, the time at which it is predicted to occur, and the direction from which the shadow will approach. The calendar functions of the mechanism are another important aspect of its design. The Greek world used a variety of different calendars, with different city-states and regions using different month names, different starting points, and different methods for reconciling the lunar months with the solar year. The mechanism's calendar displays reflect the specific calendrical traditions of a particular region of the Greek world, and the identification of these traditions has been an important part of the effort to determine where the mechanism was built. The research of Alexander Jones and others has shown that the month names used in the mechanism's metonic dial correspond to the calendar used in Corinth and its colonies, including Syracuse. This finding has led some scholars to suggest a connection between the mechanism and the Archimedean tradition of Syracuse, while others have pointed out that the Corinthian calendar was also used in other parts of the Greek world, including some of the colonies in northwestern Greece. The identification of the mechanism's calendar with a specific regional tradition provides important evidence for the device's provenance, but it does not definitively establish the place of manufacture. The question of the mechanism's accuracy has been investigated by comparing the predictions that the mechanism would have produced with the actual astronomical phenomena. The results of these comparisons show that the mechanism was highly accurate, with the gear ratios reproducing the astronomical periods to within a fraction of a percent of the correct values. The eclipse predictions, while not perfect, would have been sufficiently accurate to identify the months in which eclipses were likely to occur, though they would not have predicted the exact date or the exact time with the precision that modern methods can achieve. The accuracy of the mechanism's predictions is consistent with the astronomical knowledge of the Hellenistic period, and it demonstrates that the device's builders had access to the best available astronomical data, and that they were able to embody that data in the mechanism's gear ratios with impressive fidelity. The relationship between Greek mathematics and the design of the Antikythera mechanism can be understood more deeply by examining the specific mathematical principles that are embodied in the device's gear ratios. The ancient Greek mathematicians had developed a theory of ratio and proportion, formalized in books 5 and 7 of Euclid's Elements, that provided the theoretical framework for specifying the gear ratios that model the astronomical periods. The gear ratio that models the relationship between the solar year and the lunar month, for example, is the ratio 235:19, which is the metonic ratio, the number of lunar months in 19 solar years. This ratio was known to the Greek astronomers from at least the 5th century before the Common Era, when the Athenian astronomer Meton first identified the cycle, and it was used as the basis for the Greek lunisolar calendar. The mathematical sophistication required to design the mechanism's gear trains extends beyond the specification of gear ratios to the calculation of the number of teeth on each gear. The designer of the mechanism needed to find combinations of gear teeth that would produce the required ratios while also fitting within the physical constraints of the device, constraints that included the size of the mechanism's case, the minimum tooth size that could be reliably cut in bronze, and the need to avoid interference between adjacent gears. This design process, which requires the solution of systems of equations in integer arithmetic, demonstrates a level of mathematical competence that is consistent with the highest achievements of Greek mathematics. The role of the number theory tradition in the design of the mechanisms has been emphasized by several scholars. The Greek mathematicians, particularly those in the Pythagorean tradition, were deeply interested in the properties of numbers and in the relationships between numbers. The selection of the specific tooth counts for the mechanism's gears may have been guided not only by the practical requirements of the astronomical ratios, but also by mathematical considerations, such as the preference for numbers with specific properties, such as prime numbers or numbers with particular factorizations, that would produce smooth and reliable gear meshing. The influence of the Babylonian astronomical tradition on the mathematical content of the mechanism has been demonstrated by several lines of evidence. The Babylonian astronomers had developed sophisticated mathematical methods for predicting the positions of the celestial bodies, methods that used arithmetical procedures rather than the geometrical models that were preferred by the Greek astronomers. The astronomical data that is encoded in the Antikythera mechanism reflects the Babylonian observations, which had been accumulated over many centuries of systematic skywatching, and the mechanism's designers must have had access to this data, either directly or through the mediation of Greek astronomers who had incorporated the Babylonian observations into their own work. The school of Hipparchus, which was active in the 2nd century before the Common Era, is the most likely source of the astronomical data that is encoded in the mechanism. Hipparchus is known to have made extensive use of Babylonian astronomical data, incorporating it into his own models of the solar and lunar motions and using it to refine his predictions of eclipses and other astronomical phenomena. The fact that the mechanism's gear ratios encode the same astronomical periods that Hipparchus used in his calculations strongly suggests that the mechanism was designed by someone who was familiar with Hipparchus's work and possibly by someone who was trained in the astronomical tradition that Hipparchus had established. The astronomical observations of the Alexandrian school, which flourished in the centuries after Hipparchus, may also have contributed to the mechanism's design. The astronomers of Alexandria, who had access to the library and the research facilities of the Mautian, continued the tradition of astronomical observation and calculation that Hipparchus had established, refining the models of the celestial motions and developing new techniques for astronomical prediction. The mechanism's planetary display, which models the apparent motions of the 5 known planets, reflects astronomical knowledge that was being actively developed during the period when the mechanism was built, and the specific planetary models that are encoded in the mechanism may reflect the work of Alexandrian astronomers who were contemporaries of the device's builder. The tradition of Greek automata and mechanical devices provides additional context for understanding the engineering culture that produced the Antikythera mechanism. The ancient sources describe a remarkable variety of mechanical devices that were built in the Hellenistic period, including self-moving mechanical animals, automatic theatres that performed dramatic scenes using hydraulic and pneumatic mechanisms, and mechanical musical instruments that played predetermined tunes. These devices, while they served primarily an entertainment function, demonstrate that the Hellenistic engineers possessed a sophisticated understanding of mechanical principles and that they were capable of building complex, multi-component machines that performed predetermined sequences of actions. The tradition of automata building is documented most extensively in the works of Hero of Alexandria and Philo of Byzantium, both of whom wrote detailed treatises that describe the construction and the operation of mechanical devices. Philo's treatise on pneumatics, which survives in Arabic translation, describes devices that use air pressure, water pressure, and mechanical linkages to produce a variety of effects, including self-filling cups, automatic door openers, and mechanical birds that sing and drink water. The sophistication of these devices, which require precise manufacturing and careful assembly to function correctly, is consistent with the engineering tradition that produced the Antikythera mechanism. The connection between the automata tradition and the tradition of astronomical instrument making is an important one, because both traditions required the same fundamental skills: the ability to design complex mechanical systems, the ability to manufacture precision components, and the ability to assemble and calibrate multi-component devices. A craftsman who was skilled in the construction of automata would have possessed many of the skills that were needed to construct an astronomical mechanism like the Antikythera device, and it is plausible that the same workshops and the same craftsmen who built automata also built astronomical instruments. The tradition of gear-making in the ancient world, while poorly documented in the literary sources, is attested by the physical evidence of the Antikythera mechanism itself and by a small number of other surviving artifacts. A series of sundials from the Roman period, known as the Byzantine sundials, include gear mechanisms that were used to adjust the dial for different latitudes. These sundials, while much simpler than the Antikythera mechanism, demonstrate that the use of gears in precision instruments was not limited to a single device, but was part of a broader tradition of gear-based instrument making that continued into the Roman period. The question of how the gears of the Antikythera mechanism were designed is one that has been investigated by mechanical engineers who have analysed the tooth profiles of the surviving gears. The teeth of the mechanism's gears are roughly triangular in shape, a profile that is simpler and less efficient than the involute profile that is used in modern gear design. The triangular tooth profile, while it produces more friction and more wear than the involute profile, is adequate for a device that transmits relatively low forces at relatively low speeds, and it can be produced using simple cutting tools. The regularity of the tooth profiles across the mechanism's gears suggests that the teeth were cut using a consistent technique, possibly involving a template or a guide that ensured uniform spacing and shape. The transmission of Babylonian astronomical knowledge to the Greek world is one of the most important and least understood chapters in the intellectual history of the ancient Mediterranean. The Babylonian astronomers, working in the temples and the observatories of Mesopotamia, had accumulated centuries of systematic astronomical observations, recording the positions and the movements of the celestial bodies on clay tablets in the cuneiform script. This body of observational data, which extended back to at least the 8th century before the Common Era, was the most extensive body of astronomical observations available in the ancient world, and it provided the empirical foundation on which the Greek astronomical models were built. The specific channels through which Babylonian astronomical data reached the Greek world are not fully understood. The conquest of Mesopotamia by Alexander the Great in 331 before the Common Era brought the Greek and the Babylonian worlds into direct contact, and the establishment of the Seleucid dynasty in Mesopotamia created a political and cultural context in which the exchange of intellectual traditions between the two civilizations could occur. The astronomer Kydenas, who is known to the Greeks as Kydinu, is one of the few Babylonian astronomers whose work is known to have been used by the Greek astronomers, and his determination of the length of the lunar month and the synodic periods of the planets was incorporated into the Greek astronomical tradition. The role of Hipparchus as an intermediary between the Babylonian and the Greek astronomical traditions is particularly important for understanding the Antikythera mechanism. Hipparchus is known to have had access to Babylonian astronomical data, and he used this data to develop his models of the solar and the lunar motions that are the most accurate models in the pre-Ptolemaic astronomical tradition. The Antikythera mechanism's gear ratios, which encode the Hipparchian values for the solar and the lunar periods, therefore incorporate the Babylonian observational data that Hipparchus had used, creating a physical device that embodies the astronomical knowledge of two distinct civilizations, the observational tradition of Babylon and the mathematical modeling tradition of Greece. The role of the island of Rhodes in the development of Hellenistic science and technology deserves further attention. Rhodes was one of the wealthiest and most cosmopolitan cities of the Hellenistic world, with a thriving economy based on trade, shipping, and the export of luxury goods. The island's strategic location at the crossroads of the major shipping routes of the eastern Mediterranean made it a natural center for the exchange of goods, ideas, and technologies between the Greek world, the Near East, Egypt, and the western Mediterranean. The famous Colossus of Rhodes, one of the 7 wonders of the ancient world, was a monumental bronze statue that demonstrated the island's command of large-scale bronze casting technology, the same family of technologies that would have been needed for the precision casting of the mechanism's components. The core problem with the Antikythera mechanism is not what it is. The problem is what it implies. The existence of this device, a precision-geared analog computer built in the 2nd or 1st century before the Common Era, implies a level of technological sophistication in the ancient world that is far greater than anything suggested by the surviving literary and archaeological record. The mechanism is not merely an isolated masterpiece. It is evidence for a tradition of precision mechanical engineering that must have taken generations to develop and that must have produced other devices, other mechanisms, other machines that have not survived. The Antikythera mechanism is the tip of an iceberg, and the iceberg beneath it, the full scope of ancient Greek mechanical engineering, is almost entirely unknown. The physical description of the mechanism, as it has been reconstructed through decades of study, reveals a device of extraordinary complexity. The original mechanism is estimated to have contained at least 37 interlocking bronze gear wheels, though some reconstructions suggest a higher number. The gears range in size from approximately 130 millimeters in diameter for the largest to just a few millimeters for the smallest. The teeth of the gears are cut with a precision of approximately 1 millimeter, and the gear ratios embody specific astronomical periods with an accuracy that is, in some cases, better than 99.9%. The front of the mechanisms displayed 2 concentric circular scales, one showing the zodiac and the other showing the Egyptian calendar of 365 days. The pointer on the front dial tracked the position of the sun against the zodiac throughout the year, and a separate mechanism tracked the position of the moon, including the moon's varying speed in its elliptical orbit, a phenomenon known as the moon's anomaly. The modeling of the lunar anomaly is one of the most sophisticated features of the mechanism because it requires the use of a specialized gear arrangement that converts uniform circular motion into the varying speed that the moon exhibits as it moves along its elliptical path. The back of the mechanism displayed 2 spiral dials. The upper spiral showed the metonic cycle, the 19-year cycle of 235 lunar months, after which the phases of the moon repeat on approximately the same dates of the solar calendar. Within the metonic spiral, a subsidiary dial showed the calippic cycle, which corrected the metonic cycle by subtracting 1 day every 76 years. The lower spiral showed the Saros cycle, the cycle of 223 lunar months, approximately 18 years, after which the pattern of solar and lunar eclipses repeats. A subsidiary dial within the Saros spiral showed the exoligmos cycle, which is 3 Saros cycles, and which corrects for the fact that the Saros cycle is not an exact number of days. But here is the problem. The mechanism that has been recovered from the wreck represents only about 1/3 of the original device. The remaining 2/3 have either been lost, destroyed, or have corroded beyond recognition on the sea floor. The fragments that survive, numbered Fragment A through Fragment G, and several additional smaller pieces, contain enough information to reconstruct the basic functions of the mechanism, but they do not provide a complete picture. The front of the mechanism, in particular, is only partially preserved, and the specific mechanisms that tracked the positions of the planets are largely missing. The reconstruction of these missing components is one of the most challenging and most contested aspects of Antikythera mechanism research. The decoding of the mechanism has been a process that has unfolded over more than a century, and it has required the application of increasingly sophisticated analytical techniques. The earliest studies of the mechanism, conducted in the early 20th century, relied on visual examination and manual measurement. These early studies identified the presence of gear wheels and established that the device was a mechanical instrument of some kind, but they were unable to determine its specific function or to reconstruct its internal workings. The breakthrough that transformed the study of the Antikythera mechanism came in the 1950s and 60s, when the physicist Derek de Solla Price undertook a systematic investigation of the device using X-ray radiography. Price's X-ray images revealed the internal structure of the mechanism for the first time, showing the arrangement of the gear wheels, the configuration of the shafts and the bearings, and the general layout of the device's mechanical components. Price published his findings in a landmark paper in 1959, and in a more comprehensive monograph in 1974, establishing the Antikythera mechanism as a subject of serious scientific investigation and providing the foundation for all subsequent research. Price's work was pioneering, but it was limited by the resolution of the X-ray technology available to him. The X-ray images he produced were two-dimensional, and they often showed multiple layers of gears and other components superimposed on one another, making it difficult to determine the precise arrangement of the internal components. The resolution of the images was also insufficient to read the inscriptions that were known to be engraved on the surfaces of the mechanism, inscriptions that would eventually prove to be crucial for understanding the device's function. And it gets worse. The mechanism's inscriptions, which are engraved in ancient Greek letters on the bronze surfaces of the device, are extremely small, often less than 2 millimeters in height, and they are badly corroded after 2,000 years of immersion in salt water. Reading these inscriptions has required the development and the application of imaging technologies that are at the cutting edge of modern science, technologies that were not available to the earlier generations of researchers who studied the mechanism. The most important advance in the study of the Antikythera mechanism came in 2005, when a team led by the mathematician Tony Freeth and the astronomer Mike Edmonds, working as part of the Antikythera mechanism research project, applied a technique called X-ray computed tomography, or CT scanning, to the fragments of the mechanism. The CT scanning technology, which uses X-rays taken from multiple angles to construct a three-dimensional model of the object's internal structure, produced images of unprecedented clarity and detail, revealing features of the mechanism that had been invisible to all previous investigations. The CT scans revealed thousands of characters of Greek text that had been engraved on the surfaces of the mechanism, and that had been hidden by the marine incrustations and the corrosion that covered the device. These inscriptions, which constitute a kind of user's manual for the mechanism, describe its functions, its operating procedures, and the astronomical phenomena that it was designed to model. The inscriptions confirmed that the mechanism was an astronomical calculator of the kind that had been suspected by earlier researchers, and they provided specific information about the astronomical cycles and the calendrical systems that the mechanism was designed to track. The inscriptions also revealed a feature of the mechanism that had not been previously suspected. The device included a display that tracked the dates of the 4 great Pan-Hellenic athletic festivals of ancient Greece, including the Olympic Games. The Olympic dial, as it is now known, showed the 4-year cycle of the Olympic Games and the other major athletic festivals, including the Pythian Games at Delphi, the Nemean Games, and the Isthmian Games near Corinth. The inclusion of this feature in the mechanism suggests that the device was not merely a scientific instrument, but also a cultural artifact, a device that was connected to the religious and the social life of the Greek world, as well as to its astronomical knowledge. The study of the mechanism's inscriptions has continued to produce new discoveries. In 2016, a team of researchers led by Alexander Jones and Mike Edmonds published a comprehensive analysis of the inscriptions that significantly expanded the known text and that provided new information about the device's functions and its intended use. The analysis revealed that the mechanism included a display that tracked the positions of the 5 planets that were known to the ancient Greeks: Mercury, Venus, Mars, Jupiter, and Saturn, using a system of gears that modelled the complex looping paths that the planets appear to trace across the sky. The planetary display is one of the most remarkable features of the mechanism because the modelling of planetary motion was one of the most challenging problems in ancient astronomy. The planets do not move at a constant speed across the sky, and they periodically appear to reverse direction, a phenomenon known as retrograde motion that puzzled ancient astronomers and that was not adequately explained until the development of the heliocentric model of the solar system. The Antikythera mechanism modeled the apparent motions of the planets using a geocentric model that placed the Earth at the center of the cosmos, and the specific gear arrangements that were used to produce the planetary motions are among the most complex and the most mathematically sophisticated features of the device. The question of who built the Antikythera mechanism remains unanswered. No ancient source describes the specific device that was found in the shipwreck, and the identity of the builder or the builders is unknown. The most common hypothesis is that the mechanism was built on the island of Rhodes, which was a major center of astronomical research in the Hellenistic period, and which was associated with both Hipparchus and Posidonius. The month names that appear in the mechanism's calendar dials have been identified as belonging to a calendar used in Corinth and its colonies, which has led some scholars to suggest that the mechanism was built in or for a community that used the Corinthian calendar, possibly the city of Syracuse, which was a Corinthian colony and which was the home of Archimedes. But here is what makes this truly terrifying. The Antikythera mechanism is unique. No other device of comparable complexity has been found from the ancient world. This uniqueness is not because such devices were rare, but because the conditions that are necessary for the survival of a bronze mechanism over a period of 2,000 years are extremely uncommon. Bronze is a valuable metal that was routinely recycled in the ancient world, and mechanical devices that were no longer functional would typically have been melted down and recast into new objects. The survival of the Antikythera mechanism is a result of the shipwreck that preserved it on the seafloor, where it was protected from the recycling that would have destroyed it if it had remained on land. The implication is clear. The Antikythera mechanism is the sole surviving example of a technology that was probably not unique. Other mechanisms of similar complexity were almost certainly built in the ancient world, and they were almost certainly destroyed by the recycling of their bronze components. The Antikythera mechanism survives only because it sank to the bottom of the sea and was lost for 2,000 years. The mechanisms that remained on land, the mechanisms that were used, maintained, and eventually discarded by their owners, are gone, melted down and recast into coins, weapons, tools, and other objects by the people who inherited them and who did not understand or did not value the technology they contained. The implications of the mechanism's uniqueness deserve further exploration. The fact that the Antikythera mechanism is the only surviving device of its kind does not mean that it was the only device of its kind that was built. The literary evidence, as we have seen, describes multiple devices that modeled the movements of the celestial bodies, and the existence of a mature tradition of precision gear cutting, which is implied by the quality of the mechanism's gears, suggests that the tools and the skills needed to build such devices were available to multiple craftsmen over a period of many decades or even centuries. The recycling of bronze in the ancient world is a well-documented phenomenon that explains why so few ancient bronze objects have survived. Bronze was a valuable metal in the ancient world, and objects made of bronze were routinely melted down and recast when they were no longer needed. The coins, the tools, the weapons, and the sculptures that were made from recycled bronze may have included material from devices like the Antikythera mechanism, devices that were melted down because their owners no longer understood them or no longer had use for them. The Antikythera mechanism survived only because it was lost at sea, where it was protected from the recycling that would have destroyed it if it had remained on land. The scale of bronze recycling in the ancient world can be appreciated by considering the enormous quantities of bronze that were produced and consumed in the Roman period alone. The Roman Empire produced bronze coins in the billions, bronze tools and weapons in the millions, and bronze statues in the tens of thousands. The raw material for much of this production came from recycled bronze, including the bronze from Greek artifacts that were melted down by the Romans for reuse. The bronze from devices like the Antikythera mechanism, which would have been a negligible quantity relative to the total volume of bronze in circulation, would have been absorbed into this vast recycling system without leaving any trace. the question of how the tradition of precision's mechanical engineering was transmitted within the ancient world is one that has not been fully answered. The tradition must have been passed from master to apprentice through a system of training that ensured the continuity of the necessary skills and knowledge. The workshops in which devices like the Antikythera mechanism were built must have been specialized facilities, equipped with the tools and the instruments that were needed for precision metalworking, and staffed by craftsmen who had undergone years of training in the techniques of gear cutting, assembly, and calibration. The destruction of these workshops and the dispersal of their personnel during the political and economic upheavals of the late ancient period would have resulted in the loss of the skills and the knowledge that were necessary to build devices of the mechanism's complexity. The transition from the ancient to the medieval world was characterized by a dramatic contraction of the urban economies that had supported the specialized workshops of the Hellenistic and Roman periods. The cities that had been the centers of Hellenistic science and technology, including Alexandria, Pergamum, and Rhodes, experienced significant economic and demographic decline in the late Roman and early medieval periods, and the specialized workshops that had produced precision instruments and mechanical devices were among the casualties of this decline. The loss of the workshops was accompanied by the loss of the training systems, the supply chains, and the institutional support that had sustained them, and the result was the extinction of the tradition of precision mechanical engineering that had produced the Antikythera mechanism. The question of whether any elements of the Antikythera tradition were transmitted to the Islamic world, where sophisticated mechanical devices were built from the 9th century onward, is one of the most intriguing questions in the history of technology. The Islamic engineers who built water clocks, automata, and astronomical instruments in the medieval period demonstrated a command of mechanical principles that is reminiscent of the Hellenistic tradition, and some scholars have suggested that the Islamic mechanical tradition may have been influenced by Hellenistic models that were transmitted through the Byzantine Empire or through the Syriac-speaking communities of the Near East. The evidence for such a transmission is circumstantial rather than direct. The Islamic engineers who described their work in treatises and manuals did not cite Hellenistic sources, and the specific mechanisms that they used were often different from the mechanisms found in the Antikythera mechanism. However, the general approach of using mechanical devices to model astronomical phenomena, which is common to both the Hellenistic and the Islamic traditions, suggests that there may have been some form of intellectual continuity between them, even if the specific channels of transmission have not been identified. The broader question of what the Antikythera mechanism tells us about the relationship between knowledge and survival is one of the most profound questions that the device raises. The knowledge that was required to build the mechanism, the astronomical knowledge, the mathematical knowledge, and the mechanical knowledge existed in the minds of human beings and in the manuscripts and the workshops that supported their work. The mechanism itself was a physical embodiment of that knowledge, a device that translated abstract mathematical relationships into concrete mechanical motions. The survival of the device, while the knowledge that produced it was lost, creates a paradox. We possess the product of a tradition that we do not fully understand, a machine that we can examine and admire, but that we cannot fully explain, because the context that gave it meaning has been destroyed. The physical analysis of the mechanism's fragments has revealed additional details about the device's construction that illuminate the manufacturing techniques and the engineering standards of the ancient workshop that produced it. The X-ray CT scans of the fragments have shown that the gear wheels were cast as flat bronze discs and then finished by hand, with the teeth cut into the rim using a cutting tool. The regularity of the tooth spacing and the consistency of the tooth profiles suggest that the cutting was guided by some form of measuring instrument that ensured accurate spacing, though the specific nature of this instrument is unknown. The thickness of the gear wheels varies between approximately 1.5 and 2 millimeters, a dimension that is extraordinarily thin for a bronze component that must have been strong enough to transmit mechanical force without deforming or breaking. The thinness of the gears is one of the most impressive aspects of the mechanism's construction because it implies a level of control over the casting and the finishing process that is consistent with the highest standards of ancient metalworking. The ability to cast bronze discs of this thinness and to finish them to the required precision suggests the existence of specialized casting techniques and finishing tools that were developed specifically for the production of precision gear wheels. The shafts on which the gears are mounted are made of bronze or iron, and they rotate in bearings that are formed by holes drilled in the plates of the mechanism's case. The precision of the shaft diameters and the bearing holes, which must match closely to ensure smooth rotation without excessive play, is another indication of the high manufacturing standards that were applied to the mechanism's construction. The lubrication of the bearings, which would have been necessary to reduce friction and to prevent wear, was probably achieved using animal fat or vegetable oil, though no trace of lubricant has been detected in the surviving fragments. The case of the mechanism, which originally enclosed the gear train and the dial displays, was made of bronze sheet that was formed and joined to create a box-like enclosure. The sides of the case were decorated with inscriptions that described the mechanism's functions, and the front and back panels of the case carried the dial displays that showed the mechanism's astronomical output. The case also included protective covers for the front and back dials, which would have been opened to read the displays and closed to protect them when the mechanism was not in use. The mechanism was operated by turning a handle or a knob that was attached to the input shaft. The rotation of the input shaft drove the entire gear train, causing the pointers on the various dials to advance and to display the current positions of the sun, the moon, and the planets, as well as the current date in the calendrical and the eclipse cycles. The user could advance the mechanism to any desired date by turning the input shaft the appropriate number of turns, allowing the mechanism to be used as a tool for predicting future astronomical events, as well as for displaying current ones. The question of the mechanism's original appearance is one that has been addressed through the reconstruction efforts of Michael Wright, Tony Freeth, and other researchers. The original mechanism, when new and fully assembled, would have been a handsome object, with polished bronze surfaces, clearly engraved inscriptions, and precisely moving pointers that tracked the celestial motions on the beautifully marked dial scales. The device would have been a striking demonstration of Greek craftsmanship as well as Greek science, an object that would have impressed its viewers not only with the sophistication of its astronomical functions, but also with the beauty and the precision of its mechanical execution. The dating evidence for the Antikythera mechanism deserves more detailed examination because the date of the device's construction is an important factor in determining who might have built it and what astronomical knowledge was available to its builder. The primary dating evidence comes from two sources: the artifacts found in the shipwreck and the astronomical calibration of the mechanism itself. The artifacts from the shipwreck, which include pottery, coins, glassware, and other datable objects, suggest that the ship sank in approximately 70 to 60 before the Common Era. The pottery styles and the coin types are consistent with a date in the 1st century before the Common Era, and the overall character of the cargo suggests a wealthy ship of the late Hellenistic or early Roman period. The astronomical calibration of the mechanism provides a different kind of dating evidence. The mechanism's eclipse prediction display, which uses the Saros cycle to predict the dates of future eclipses, appears to be calibrated to a starting date that corresponds to a specific eclipse in the historical record. The analysis of the eclipse data encoded in the mechanism has suggested several possible starting dates, with the most commonly cited being an eclipse that occurred in approximately 205 or 187 before the Common Era. If these dating analyses are correct, the mechanism was designed or calibrated several decades before the ship that carried it sank, suggesting that the device was already an antique when it was loaded onto the vessel. The discrepancy between the shipwreck date and the astronomical calibration date has led some scholars to suggest that the mechanism was built in the 2nd century before the Common Era and was subsequently owned and used for several decades before being loaded onto the ship that carried it to its resting place on the seafloor. This hypothesis is consistent with the literary evidence, which describes the construction of astronomical mechanisms in the period of Archimedes and Hipparchus, and with the physical evidence of the mechanism itself, which shows signs of wear and repair that are consistent with prolonged use. The specific astronomical model that the mechanism uses for the solar and lunar motions has been the subject of detailed analysis by astronomers who have compared the mechanism's predictions with the actual positions of the Sun and the Moon at various dates in the 2nd and 1st centuries before the Common Era. These analyses have confirmed that the mechanism's solar model is consistent with the simple model of uniform circular motion that was used by the Greek astronomers before the development of the more sophisticated models of Hipparchus and Ptolemy. The lunar model, which includes the pin and slot mechanism for the anomaly, is consistent with the model of epicyclic motion that was developed by Hipparchus, suggesting that the mechanism's builder had access to Hipparchus's work on the lunar motion. The inscriptions on the mechanism have been analysed by epigraphers who have studied the letter forms, the spelling conventions, and the vocabulary of the text. The epigraphic analysis has confirmed that the inscriptions were written in the Koine Greek that was the common language of the Hellenistic world, and the letter forms are consistent with a date in the 2nd or 1st century before the Common Era. The vocabulary of the inscriptions includes technical astronomical terms that are consistent with the astronomical terminology that was in use during this period, and the phrasing of the descriptions suggests that the inscriptions were written for an audience that was familiar with the basic concepts of Greek astronomy, but that was not necessarily composed of professional astronomers. The provenance of the mechanism, the question of where it was built and for whom, remains one of the most debated questions in Antikythera research. The Corinthian month names on the calendar dial, the astronomical data from the Hipparchian tradition, the Rhodian origin suggested by the connection to Hipparchus and Posidonius, and the Syracusan connection suggested by the Archimedean tradition, all provide evidence that points in different directions. The most likely scenario is that the mechanism was built by a craftsman or a workshop that was connected to the astronomical tradition of the Eastern Mediterranean, possibly on Rhodes or in one of the other major centres of Hellenistic science, and that it was commissioned by a patron who was interested in astronomical modelling and who had the wealth to fund the construction of a complex and expensive device. The question of the mechanism's intended user is one that has implications for our understanding of the device's cultural significance. The inscriptions on the mechanism, which describe its functions in language that is accessible to an educated layperson, suggest that the device was not intended solely for professional astronomers, but was designed for a broader audience that included educated citizens who were interested in astronomy and who could appreciate the device's modelling of the celestial motions. The concept of the educated layperson in the Hellenistic world is an important one for understanding the cultural context of the mechanism. The Hellenistic period was characterized by a widespread interest in science, philosophy, and natural phenomena among the educated elite, and the popularization of scientific knowledge through lectures, demonstrations, and the production of accessible texts was a significant feature of Hellenistic intellectual culture. The Antikythera mechanism may have been a product of this culture of scientific popularization, a device that was designed to demonstrate the order and the regularity of the celestial motions to an audience that was interested in understanding the cosmos, but that did not necessarily possess the mathematical skills needed to perform the astronomical calculations that the mechanism performed mechanically. The question of the mechanism's price and its accessibility is one that scholars have considered. The construction of the mechanism would have required a significant investment of time, materials, and skilled labour. The bronze needed for the gears, the case, and the other components was a valuable material, and the labour of the skilled craftsmen who cut the gears, assembled the mechanism, and calibrated its displays would have been expensive. A rough estimate of the mechanism's cost, based on the quantity of bronze used and the amount of skilled labor required, suggests that the device would have been affordable only for wealthy individuals or institutions. The mechanism was, in all probability, a luxury object owned by a member of the elite who had both the intellectual interest and the financial resources to commission and to maintain such a device. The question of how the mechanism was maintained and repaired is one that has received less attention than the question of how it was built, but it is important for understanding the device's operational history. A gear-driven mechanism of this complexity requires periodic maintenance, including the cleaning of the gear teeth, the lubrication of the bearings, and the replacement of components that become worn or damaged through use. The mechanism's owner would have needed access to a skilled craftsman who could perform this maintenance, and the availability of such craftsmen would have been limited to the major cities and the specialized workshops of the Hellenistic world. The evidence that the mechanism had been repaired during its operational life comes from the physical examination of the fragments, which has revealed signs of modification and repair that are consistent with the device having been used and maintained over a period of years or decades. Some of the gear teeth show signs of wear that are consistent with regular use, and some of the components appear to have been replaced or modified, possibly to correct errors or to update the device's astronomical calibration. These signs of use and repair suggest that the mechanism was not a display piece or a demonstration model, but a working instrument that was regularly used and maintained by its owner. The question of why the mechanism was on the ship that sank near Antikythera is one that has been the subject of considerable speculation. The ship's cargo, which included luxury goods, works of art, and other valuable objects, suggests that the vessel was carrying the possessions of a wealthy individual or the inventory of a merchant who dealt in luxury goods. The mechanism may have been part of the personal collection of a wealthy Roman who was transporting Greek cultural treasures to Italy, or it may have been part of a merchant's inventory intended for sale to a wealthy buyer in Rome or another Italian city. The possibility that the mechanism was among the spoils of war, seized from a Greek city or a Greek patron by a Roman military commander, is another hypothesis that has been considered. The Roman conquest of the Greek world, which was completed in the 1st century before the Common Era, was accompanied by the systematic looting of Greek cultural treasures, including works of art, manuscripts, and scientific instruments. The Roman generals and politicians who participated in the conquest often displayed their looted treasures in public, and the transfer of Greek cultural objects to Rome was a major feature of the cultural interaction between the Greek and the Roman worlds. The investigation of the mechanism's materials using modern analytical chemistry has provided additional information about the manufacturing process and the sources of the raw materials. The bronze alloy used in the mechanism's gears contains approximately 95% copper and 5% tin, a composition that is typical of the tin bronzes that were widely used in the Hellenistic and Roman periods. The tin-bronze alloy has good casting properties, adequate strength, and sufficient hardness for the cutting of gear teeth, making it well suited for the construction of precision mechanical components. The trace elements present in the bronze, including small quantities of lead, arsenic, and other metals, provide information about the origin of the copper ore that was used to produce the alloy. The analysis of these trace elements is an ongoing area of research, and the results may eventually help to determine the geographical origin of the mechanism's materials and, by extension, the location of the workshop in which it was built. The construction of the mechanism required not only the precision cutting of gear teeth, but also the accurate drilling of holes for the shafts and bearings, the forming of bronze sheet for the case and the dial plates, and the engraving of the thousands of characters of text that are inscribed on the mechanism's surfaces. Each of these operations required specialized tools and techniques that imply a well-equipped workshop with access to a range of metalworking instruments, including files, saws, drills, engraving tools, and measuring instruments. The engraving of the mechanism's inscriptions is itself a remarkable feat of craftsmanship. The letters, which are typically less than 2 millimeters in height, are engraved with a precision and a consistency that demonstrate a high level of skill in the art of letter cutting. The engraver, who produced the inscriptions, must have been trained in the art of writing small-scale text on metal surfaces, a specialized skill that was associated with the production of coins, seals, and other objects that required miniature inscription work. The question of how many people were involved in the construction of the mechanism is one that cannot be answered with certainty, but the range of skills that the construction required suggests that it was a collaborative effort involving multiple craftsmen with different specializations. The designer of the mechanism, who specified the gear ratios and the mechanical arrangements, was almost certainly an astronomer or a mathematician who possessed a deep understanding of the celestial motions. The craftsmen who manufactured the gears, the shafts, the bearings, and the other mechanical components were skilled metalworkers who specialized in precision manufacturing. The engraver who inscribed the text was a specialist in miniature lettering, and the assembler who put the completed components together and calibrated the mechanism was a skilled technician who understood the workings of the device as a whole. The collaborative nature of the mechanism's construction is consistent with the organization of Hellenistic workshops, which typically employed teams of craftsmen with different specializations who worked together on complex projects under the supervision of a master craftsman or an engineer. The construction of a device as complex as the Antikythera mechanism would have required the coordinated effort of a team of specialists, and the quality of the finished product reflects then the high standards that were maintained by the best workshops of the Hellenistic period. The study of the mechanism's calendar system has revealed information about the specific community for which the device was built. The Corinthian calendar that is inscribed on the mechanism is used in Corinth and its colonies, including the important city of Syracuse in Sicily. The identification of the calendar has led to two competing hypotheses about the mechanism's origin. The first hypothesis, which emphasizes the connection to Syracuse, points to the city's association with Archimedes and with the tradition of mechanical astronomical modeling that is attributed to him. The second hypothesis, which emphasizes the broader distribution of the Corinthian calendar, points to other communities that use this calendar, including some on the Greek mainland and in northwestern Greece. The discovery that the mechanism includes a dial for the Olympic Games and the other Panhellenic festivals has added a new dimension to the discussion of the device's cultural context. The Panhellenic festivals were among the most important cultural institutions of the ancient Greek world, and their inclusion on the mechanism suggests that the device was intended for use by a Greek-speaking community that participated in these festivals. The Olympic Games dial is particularly significant because it demonstrates that the mechanism was not purely an astronomical instrument, but also a cultural artifact, a device that connected the cycles of the cosmos to the cycles of human, social, and religious life. The month names inscribed on the metonic dial of the mechanism have been identified as Corinthian month names, but a subsidiary display on the mechanisms includes month names from a different calendar that has been identified as Egyptian. The inclusion of the Egyptian calendar, which was a standardized and widely recognized calendar of 12 months of 30 days each, plus 5 additional days, reflects the influence of the Alexandrian astronomical tradition, which used the Egyptian calendar as a standard reference for astronomical calculations. The presence of both Corinthian and Egyptian calendar elements in the mechanism suggests a connection to the broader Mediterranean world and to the tradition of astronomical calculation that was centered in Alexandria. The mechanism's back dials, which display the metonic and the Saros cycles, are arranged in spiral patterns that allow the user to track these multi-year cycles by following a pointer along the spiral from the center to the periphery. The spiral arrangement is an ingenious solution to the problem of displaying long-period cycles on a compact dial because it allows a cycle of many years to be displayed on a single dial by winding the scale around itself in a spiral that occupies less space than a linear scale would. The use of the spiral arrangement in the mechanism is unique among ancient instruments, and it represents a creative approach to the design challenge of displaying complex astronomical data in a compact and readable format. The attempt to understand the Antikythera mechanism fully, to reconstruct its complete original form, and to identify the full range of its functions, has been one of the great scientific detective stories of the modern era. The investigation has drawn on expertise from a remarkable range of disciplines, including astronomy, mathematics, physics, engineering, classical philology, archaeology, and computer science, and it has required the development and the application of technologies that are at the forefront of modern science. The story of the mechanism's decoding is a story of incremental progress, of hypotheses proposed and tested and revised, of new technologies revealing features that were invisible to earlier methods, and of a growing appreciation of the sophistication and the ambition of the ancient device. The first major attempt at reconstruction, which was undertaken by Derek de Solla Price in the 1950s and 60s, established the basic framework for understanding the mechanism, but left many questions unanswered. Price identified the main gear train that drove the solar and lunar displays on the front of the mechanism, and he determined that the device was an astronomical calculator that modeled the movements of the sun and the moon. But Price's reconstruction was incomplete, partly because the X-ray technology available to him was insufficient to resolve the fine details of the mechanism's internal structure, and partly because he was working with fragments that represented only a fraction of the original device. The second major phase of investigation began in the late 1980s and continued through the 1990s, when a team led by the Australian computer scientist Alan Bromley and the clockmaker Frank Percival undertook a new study of the mechanism using improved X-ray techniques. Bromley and Percival's work produced better images of the mechanism's internal structure and led to the identification of several features that had not been recognized by Price, including additional gear wheels and a more complex arrangement of the back dials than Price had proposed. Bromley's premature death in 2002 left his work incomplete, but his contributions laid the groundwork for the major advances that followed. The third and most productive phase of investigation began in 2005 with the work of the Antikythera Mechanism Research Project, the international team led by Tony Freeth and Mike Edmonds that applied CT scanning to the mechanism's fragments. The CT scans, which were performed using a custom-built X-ray CT system provided by X-Tech Systems, now part of Nikon, produced three-dimensional images of the mechanism's internal structure at a resolution that revealed individual gear teeth, the shafts and bearings that supported the gears, and the thousands of characters of Greek text that were engraved on the device's surfaces. The results of the CT scanning were revolutionary. The scans revealed that the mechanism was far more complex than any previous investigation had suggested, with more gear wheels and more displays, functions than had been previously identified. The scans revealed the full text of the inscriptions on the mechanism, which provided specific information about the device functions and its intended use, and the scans revealed the specific gear ratios that were used in the mechanism, allowing researchers to determine with precision the astronomical periods that the device was designed to model. The reconstruction of the mechanism's planetary displays has been one of the most challenging and most controversial aspects of the research. The front of the mechanism included a display that showed the positions of the 5 known planets against the zodiac, but the specific gear arrangements that produced the planetary motions are largely missing from the surviving fragments. Several different reconstructions have been proposed, each using different gear arrangements to model the planetary motions, and the debate over which reconstruction is correct continues. The reconstruction proposed by Tony Freeth in 2021 is the most ambitious and the most complete proposal to date. Freeth's reconstruction uses a system of nested gear rings and pin and slot mechanisms to model the epicyclic motions of all 5 planets, as well as the Sun and the Moon, on the front display of the mechanism. The reconstruction is consistent with the surviving physical evidence and with the information provided by the inscriptions, and it represents a plausible and elegant solution to the problem of the planetary display. But it has not been universally accepted by other researchers, and the question of how the original mechanism modelled planetary motion remains open. The numbers are striking when we consider the precision of the mechanism's gear ratios. The gear ratio that models the metonic cycle, for example, uses gears with 53 and 127 teeth to produce a ratio of 127 to 53, which equals approximately 2.396226. This ratio represents the number of tropical months in 1 year of the metonic cycle, and it is accurate to within 1 part in approximately 40,000. The gear ratios for the other astronomical cycles are similarly precise, demonstrating that the mechanism's builders possessed a sophisticated understanding of the mathematical relationships that govern the movements of the celestial bodies and the ability to embody those relationships in precision-cut bronze gears. The pin and slot mechanism that models the moon's anomaly is one of the most ingenious features of the device. The moon does not move at a constant speed in its orbit. It moves faster when it is closer to the Earth and slower when it is farther away, a consequence of the elliptical shape of its orbit. The Antikythera mechanism models this varying speed using a gear that is mounted slightly off-center on its shaft, so that as it rotates, a pin on its surface engages with a slot on an adjacent gear, converting the uniform rotation of one gear into the varying rotation of the other. This pin and slot mechanism is a brilliant piece of mechanical engineering that demonstrates a deep understanding of both the astronomical phenomenon it models and the mechanical principles needed to reproduce it. The question of what tools and techniques were used to build the mechanism is one that has been investigated by mechanical engineers and historians of technology. The gear teeth of the mechanism are cut with a regularity and a precision that suggest the use of some form of mechanical dividing instrument, a device that could divide a circle into equal parts and that could guide the cutting of gear teeth at regular intervals. The existence of such instruments in the ancient world is not documented in any surviving literary source, but the physical evidence of the mechanism itself strongly implies that they existed. The mechanism could not have been built without them. The metallurgical analysis of the mechanism's components has provided additional information about the manufacturing techniques that were used. The bronze alloy from which the gears are made is a tin bronze, a composition that is consistent with the bronze working tradition of the Hellenistic period. The gears appear to have been cast as flat discs and then hand-finished, with the teeth cut into the rim using a tool such as a file or a saw. The precision of the cutting, which is consistent across all the surviving gears, suggests a high level of skill and a systematic approach to manufacture that implies training, experience, and possibly the use of jigs or guides. The question of whether the Antikythera mechanism was a unique creation or a product of a manufacturing tradition is one of the most important questions in the study of the device. If the mechanism was a unique creation, the work of a single genius or a small group of exceptionally skilled craftsmen, then its loss would represent the extinction of a technology that existed in only a single example. If the mechanism was a product of a manufacturing tradition, a tradition that produced multiple devices of similar complexity, then the loss would be even more significant, because it would mean that an entire tradition of precision mechanical engineering was lost when the ancient world declined. The literary evidence supports the latter interpretation. As we have noted, Cicero described mechanical devices built by Archimedes that modelled the movements of the celestial bodies, and he described a similar device built by Posidonius. The Roman writer Ovid, in his description of the mythological palace of the sun, used language that some scholars have interpreted as a description of a mechanical orrery similar to the Antikythera mechanism. The Byzantine scholar Procopius described a mechanical device that was used to calculate the dates of Easter, a device that may have been a descendant of the Antikythera tradition. These literary references suggest that mechanical astronomical devices were known in the ancient world, and that the Antikythera mechanism was not an isolated creation, but a product of a broader tradition of mechanical astronomical modelling. The question of why this tradition was lost is one of the most important questions in the history of technology. The transition from the ancient to the medieval world, which occurred over a period of several centuries, was accompanied by a dramatic decline in the level of technological sophistication in the West. The precision metalworking techniques that were required to build devices, like the Antikythera mechanism, were not maintained in the medieval period, and the mathematical and astronomical knowledge that informed the mechanism's design was partially lost, along with the manuscript traditions that preserved it. The recovery of gear-based mechanical computing in the medieval Islamic world, where astronomers built astrolabes and mechanical calendrical devices, and later in medieval Europe, where clockmakers developed the mechanical clock, represents a reinvention rather than a continuation of the ancient tradition. The medieval Islamic astronomical tradition is particularly relevant to the question of technological continuity. Islamic astronomers and engineers built sophisticated mechanical devices, including water clocks, automata, and astronomical instruments that display some of the same mechanical principles that are found in the Antikythera mechanism. The question of whether these Islamic devices represent an independent invention or a continuation of the ancient Greek tradition, transmitted through channels that have not been fully identified, is one that scholars continue to debate. The existence of the Antikythera mechanism raises the possibility that some elements of the ancient mechanical tradition may have been transmitted to the Islamic world through channels such as the Byzantine Empire or the Syriac-speaking communities of the Near East that have not been fully explored. The comparison between the Antikythera mechanism and the mechanical clocks that were developed in medieval Europe in the 13th and 14th centuries is instructive. The earliest mechanical clocks used gear trains and escapement mechanisms to mark the passage of time, and some of the more ambitious clock designs included astronomical displays that showed the positions of the sun, the moon, and the planets. These clocks represent the earliest known European use of gear-based mechanical computing, and they have traditionally been regarded as the starting point of the Western tradition of precision mechanical engineering. The discovery of the Antikythera mechanism has pushed the history of gear-based computing back by over 1,000 years, revealing that the tradition that produced the medieval clocks had an ancient precursor that was at least as sophisticated as the medieval devices themselves. The modern replicas and reconstructions of the Antikythera mechanism that have been built by engineers and craftsmen around the world provide practical evidence for the feasibility of the ancient technology. Several working replicas have been constructed using the methods and the materials that would have been available to the ancient builders, and these replicas demonstrate that the mechanism's gears can be cut with sufficient precision using hand tools, and that the device functions as its builders intended. The most famous of these replicas is the reconstruction built by the Australian craftsman Michael Wright, who spent years studying the mechanism and building a working model that demonstrates its astronomical functions. The ongoing underwater archaeological investigation of the Antikythera shipwreck site has produced additional discoveries that have enriched our understanding of the mechanism and the world that produced it. Return expeditions to the wreck site, conducted in 2012 and subsequently, have recovered additional artifacts from the ship, including bronze and marble statues, ceramics, and other objects that provide evidence for the cargo and the provenance of the vessel. The expeditions have also recovered additional fragments of corroded bronze that may or may not be parts of the mechanism itself, fragments that are currently being analysed using CT scanning and other techniques. The possibility that additional fragments of the mechanism may still lie on the seafloor at the wreck site is one that continues to motivate archaeological investigation. The development of new imaging technologies continues to reveal previously unknown features of the mechanism. The application of polynomial texture mapping, a technique that uses multiple photographs taken under different lighting conditions to reveal surface details that are invisible under ordinary illumination, has been used to read inscriptions and to identify surface features on the mechanism's fragments that were not visible in the CT scans. The combination of CT scanning, polynomial texture mapping, and other imaging techniques has created a comprehensive dataset of information about the mechanisms that is far more detailed and far more complete than anything that was available to earlier generations of researchers. The collaborative and interdisciplinary nature of the Antikythera mechanism research project is itself a significant aspect of the story. The study of the mechanism has required the collaboration of experts in astronomy, mathematics, mechanical engineering, classical philology, epigraphy, archaeology, and computer science, and the project has demonstrated the value of interdisciplinary research in addressing complex problems that transcend the boundaries of any single academic discipline. The success of the project in decoding the mechanism's functions and in reconstructing its original form has been a product of the combined expertise of researchers from multiple fields working together toward a common goal. The role of underwater archaeology in the discovery and the study of the Antikythera mechanism has been one of the most important aspects of the device's history. The Antikythera shipwreck, which was discovered in 1900 by sponge divers working off the coast of Antikythera, was one of the first underwater archaeological sites to be systematically investigated, and the discoveries made at the site have had a profound impact on the development of underwater archaeology as a discipline. The original recovery of the artifacts from the wreck was conducted under difficult and dangerous conditions. The divers who recovered the artifacts worked at depths of approximately 40 to 50 meters using surface-supplied air and heavy diving suits that limited their mobility and their time on the bottom. The conditions at the wreck site were challenging, with strong currents, poor visibility, and the constant risk of decompression sickness, which struck several of the divers during the recovery operations. Despite these challenges, the divers recovered a remarkable collection of artifacts, including bronze and marble statues, pottery, glassware, coins, and the corroded mechanism that would eventually be identified as the Antikythera mechanism. The return expeditions to the Antikythera wreck site that have been conducted since 2012 have used modern diving technology, including rebreather systems and robotic diving suits, to investigate the site with a thoroughness and a precision that were not possible during the original recovery. These modern expeditions have recovered additional artifacts from the wreck, including a bronze arm from a statue, fragments of bronze and marble sculpture, and additional corroded bronze objects that may or may not be parts of the mechanism. The expeditions have also produced detailed maps and three-dimensional models of the wreck site that have provided new information about the ship's cargo, its structure, and the circumstances of its sinking. The question of whether additional fragments of the mechanism remain on the sea floor is one that has motivated continued investigation of the wreck site. The surviving fragments of the mechanism represent only about a third of the original device, and the remaining 2/3 are either lost or awaiting discovery on the seafloor. The seafloor in the vicinity of the wreck is covered with a thick layer of sediment and marine growth that could conceal additional fragments, and the use of metal detectors and other surveying instruments has identified anomalies in the sediment that may represent buried metallic objects. The recovery and the analysis of any additional fragments would significantly advance our understanding of the mechanism, potentially resolving the outstanding questions about the planetary display and the other missing functions. The conservation of the Antikythera mechanism fragments has been an ongoing challenge for the National Archaeological Museum in Athens, which is responsible for the preservation and the display of the device. The fragments are made of bronze that has been severely corroded by 2,000 years of immersion in salt water, and the conservation of these fragile objects requires specialized techniques and equipment. The conservation process has included the careful removal of marine incrustations, the stabilization of the corroded metal, and the application of protective coatings that slow the rate of further deterioration. The conservation work has also involved the production of detailed photographic and three-dimensional records of the fragments, ensuring that the information they contain is preserved even if the physical objects themselves deteriorate further. The impact of the Antikythera mechanism on popular culture has been significant, and the device has inspired numerous works of fiction, documentary films, museum exhibitions, and popular science publications. The mechanism's combination of antiquity, complexity, and mystery has made it an irresistible subject for writers and filmmakers who are interested in the history of technology and the capabilities of the ancient world. The popular interest in the mechanism has, in turn, supported the scientific research that has been conducted on the device by generating public awareness and by attracting funding for the ongoing investigation. The museum exhibitions that have featured the Antikythera mechanism and its replicas have been among the most popular exhibitions in the history of the museums that have hosted them. The permanent exhibition at the National Archaeological Museum in Athens, which displays the original fragments alongside explanatory models and multimedia presentations, attracts thousands of visitors each year and is one of the most visited exhibits in the museum. Temporary exhibitions of mechanism replicas and related materials have been held in museums around the world, introducing the device to audiences that would not otherwise have the opportunity to see the original fragments. The educational value of the Antikythera mechanism is considerable, and the device has been used as a teaching tool in courses on the history of science, the history of technology, and classical studies. The mechanism provides a concrete and tangible example of the achievements of ancient science and technology, and its study requires the integration of knowledge from multiple disciplines, making it an ideal subject for interdisciplinary education. The mechanism's complexity and its mysterious origins also make it an engaging subject for students, who are often fascinated by the idea that the ancient world was capable of building a device that would not be matched for over 1,000 years. The philosophical implications of the mechanisms extend beyond the specific questions of who built it and how it worked. The mechanism raises fundamental questions about the nature of knowledge, the relationship between theory and practice, and the conditions that are necessary for the development and the maintenance of sophisticated technology. The device is a physical demonstration of the proposition that abstract mathematical and astronomical knowledge can be translated into concrete mechanical form, and its existence 2,000 years ago challenges the assumption that this kind of translation is a modern phenomenon. The question of whether the mechanism's builders regarded it as a scientific instrument, an educational tool, a display piece, or a sacred object is one that has been debated by scholars. The inclusion of the Olympic Games dial suggests that the mechanism had a cultural function that extended beyond pure astronomical calculation, connecting the cycles of the cosmos to the human cycles of festival and competition. The inscriptions on the mechanism, which describe its functions in language that is accessible to an educated layperson rather than a specialist, suggests that the device was intended for a relatively broad audience rather than for the exclusive use of professional astronomers. The mechanism may have been a device for demonstration and instruction, a tool for showing an educated audience how the cosmos worked and how the celestial cycles governed the calendar and the religious festivals. In this interpretation, the mechanism was not merely a calculator but a teaching device, a three-dimensional textbook that made the abstract mathematical relationships of astronomy concrete and visible. The mechanism's design, which presents its astronomical information on clearly labeled dials with rotating pointers, is consistent with this interpretation because it presents the device's output in a format that is immediately comprehensible to anyone who can read the dial labels without requiring specialized knowledge of the underlying mathematical models. The comparison between the Antikythera mechanism and the astronomical clocks of medieval Europe provides additional perspective on the mechanism's cultural significance. The great astronomical clocks that were built in European cathedrals and town halls in the 14th and 15th centuries, such as the astronomical clock in Strasbourg Cathedral and the clock in Prague's Old Town Square, served a similar function, displaying astronomical information to the public in a format that connected the cycles of the cosmos to the cycles of the Christian calendar and the liturgical year. These clocks were objects of civic pride and cultural significance, and they demonstrate that the desire to build mechanical models of the cosmos was not unique to the ancient Greeks, but was a persistent feature of human culture across different civilizations and different eras. The specific details of the pin and slot mechanism that models the lunar anomaly deserve closer examination, because this mechanism is one of the most ingenious and most instructive features of the device. The lunar anomaly, the variation in the moon's speed as it moves along its elliptical orbit, was known to the ancient Greek astronomers, who modelled it using the geometric concept of the epicycle, a small circle whose centre moves along a larger circle. The pin and slot mechanism in the Antikythera mechanism translates this geometric model into a mechanical motion using a pin that is mounted on one gear to engage with a slot that is cut in an adjacent gear. The pin is mounted on a gear that rotates at the rate of the moon's anomalistic period, the time it takes for the moon to travel from its closest approach to the Earth, known as perigee, back to perigee again. The slot is cut in a gear that rotates at a slightly different rate, the rate of the moon's sidereal period. The engagement of the pin with the slot converts the uniform rotation of the first gear into a varying rotation of the second gear, reproducing the variation in the moon's speed that is caused by the eccentricity of its orbit. The result is a mechanical output that closely approximates the moon's actual motion, with the moon moving faster at perigee and slower at apogee, exactly as it does in the sky. The pin and slot mechanism is an exceptionally elegant solution to a complex engineering problem. The conversion of uniform circular motion into varying circular motion is not a trivial mechanical challenge, and the pin and slot mechanism achieves it with a minimum of components and a maximum of reliability. The mechanism uses only 2 additional gears beyond those that would be needed for a simple lunar display, and it produces a motion that is accurate to within a few % of the actual lunar motion. The elegance and the efficiency of the solution suggest that the mechanism's designer was not only a skilled astronomer, but also a gifted mechanical engineer, someone who understood both the astronomical problem and the mechanical means of solving it. The question of whether similar pin and slot mechanisms were used in the planetary displays of the mechanism is one that remains open. The surviving fragments of the planetary display are insufficient to determine definitively whether pin and slot mechanisms were used to model the anomalies of the planetary motions, but the reconstruction proposed by Tony Freeth in 2021 uses a system of pin and slot mechanisms in combination with other gear arrangements to model the varying speeds of the planets. If Freeth's reconstruction is correct, the mechanism would have used a total of several dozen gears to model the motions of all 7 celestial bodies that were known to the ancient Greeks. The comparison between the Antikythera mechanism and other ancient devices that modelled astronomical phenomena is important for understanding the mechanism's place in the history of technology. The armillary sphere, which was used by ancient astronomers to model the celestial sphere and to measure the positions of the stars, is one of the oldest known astronomical instruments. The astrolabe, which was developed in the Hellenistic period and which was widely used in the Islamic world and in medieval Europe, is another device that modelled astronomical phenomena using a combination of mathematical principles and mechanical construction. But neither the armillary sphere nor the astrolabe uses gears, and neither is capable of the dynamic modelling that the Antikythera mechanism achieves. The mechanism's use of gear-driven displays that move continuously as the input shaft is turned sets it apart from all other known ancient astronomical instruments and establishes it as a fundamentally different type of device. The question of whether the mechanism was capable of modelling phenomena that go beyond the astronomical functions that have been identified is one that has been raised by some researchers. The inscriptions on the mechanisms describe its astronomical functions in considerable detail, and it is possible that the device included additional functions that are not described in the inscriptions that have been recovered. The missing portions of the mechanism, which constitute approximately 2/3 of the original device, may have included displays and functions that have not been identified in the surviving fragments, and the possibility that the mechanism was even more complex than the current reconstruction suggests cannot be ruled out. The role of the Antikythera mechanism in the history of computing has been recognized by computer scientists and historians of technology who have placed the device in the broader context of the development of computational machines. The mechanism is generally regarded as the earliest known example of an analog computer, a machine that uses physical quantities, in this case the angles of rotation of gear wheels, to represent and to compute mathematical quantities. The tradition of analog computing continued through the medieval period, with the development of astrolabes and other gear-driven instruments, and into the modern era with the development of slide rules, planimeters, differential analyzers, and other analog computing devices that were widely used in science and engineering before the advent of the digital computer. The transition from analog to digital computing in the 20th century was one of the most important technological transitions in human history, and the Antikythera mechanism provides a historical perspective on this transition that is both illuminating and sobering. The analog computing tradition that the mechanism represents, a tradition that used physical mechanisms to model the mathematical relationships, was productive and successful for over 2 millennia. The digital computing tradition, which uses electronic circuits to process information in the form of binary digits, has been productive for less than a century. The comparison between the two traditions reminds us that the digital computing paradigm that dominates our world today is not the only way to build computational machines, and that alternative approaches to computation, including approaches based on mechanical principles, have been productive and successful in the past. The reception of the Antikythera mechanism in the broader scientific community has evolved significantly since its discovery. In the early 20th century, when the mechanism was first identified as a gear-driven device, the reaction of the scholarly community was largely one of disbelief and skepticism. Many scholars found it difficult to accept that the ancient Greeks were capable of building a device of such complexity, and the mechanism was dismissed by some as a medieval device that had been accidentally associated with the ancient shipwreck, or as a much simpler device that had been overinterpreted by enthusiastic but misguided researchers. The work of Derek de Solla Price in the 1950s and 60s began to change this perception by providing rigorous scientific evidence for the mechanism's complexity and its ancient date. Price's X-ray studies demonstrated beyond doubt that the mechanism contained precision-cut gear wheels that were arranged in a complex train, and his analysis of the gear ratios showed that the device was designed to model specific astronomical periods with high accuracy. Price's work established the Antikythera mechanism as a legitimate subject of scientific study and laid the foundation for the more advanced investigations that would follow. The CT scanning work of the Antikythera Mechanism Research Project in the 2000s produced a further shift in the scholarly perception of the device by revealing features that were even more complex and more sophisticated than Price had documented. The discovery of the mechanism's inscriptions, the identification of the planetary display, and the reconstruction of the mechanism's full range of astronomical functions all contributed to a growing appreciation of the device's complexity and a growing recognition that the ancient Greeks were capable of feats of engineering that had previously been thought impossible. The current scholarly consensus on the Antikythera mechanism is that it is a genuine product of the Hellenistic period, built in approximately the 2nd or 1st century before the Common Era, and that it represents a level of technological sophistication that is consistent with the highest achievements of Hellenistic science and engineering. This consensus, which is supported by the physical evidence of the mechanism itself, the CT scanning data, the epigraphic analysis of the inscriptions, and the archaeological context of the shipwreck, represents a fundamental revision of the historical understanding of ancient Greek technology. The impact of the Antikythera mechanism on the broader historical narrative of Western technology has been profound. Before the discovery and the decoding of the mechanisms, The history of Western technology was typically presented as a story of continuous progress, beginning with the simple tools of the Neolithic period and advancing through the innovations of the ancient, medieval, and modern periods to the sophisticated technologies of the present day. The Antikythera mechanism complicates this narrative by demonstrating that the ancient world achieved a level of technological sophistication that was subsequently lost, and that was not recovered for over 1,000 years. The mechanism provides concrete evidence for the concept of technological regression, the idea that technologies can be developed and then lost, and it challenges the assumption that technological progress is a one-way process. The study of the Antikythera mechanism has raised important questions about the nature of ancient scientific knowledge and its relationship to the modern scientific tradition. The mechanism demonstrates that the ancient Greeks possessed a body of astronomical knowledge that was comprehensive, mathematically sophisticated, and capable of being applied to the construction of precision instruments. The question of whether this knowledge constitutes science in the modern sense of the word, and the question of how the ancient scientific tradition relates to the modern tradition that emerged in the 16th and 17th centuries are questions that have been debated by historians and philosophers of science. The traditional view, which was articulated by historians of science in the early 20th century, held that the ancient Greeks were primarily interested in theoretical and philosophical questions about the nature of the cosmos, and that they were less interested in the practical application of their knowledge to the construction of instruments and machines. The Antikythera mechanism challenges this view by demonstrating that at least some ancient Greek scientists were deeply interested in the practical application of their knowledge, and that they possessed the skills and the resources needed to translate their theoretical understanding into physical form. The concept of applied astronomy, the use of astronomical knowledge for practical purposes such as calendar keeping, navigation, and the prediction of eclipses, was well established in the ancient world, and the Antikythera mechanism is the most sophisticated surviving example of this tradition. The device demonstrates that the application of astronomical knowledge to practical problems was not a modern innovation but an ancient practice, and that the ancient tradition of applied astronomy was capable of producing devices of extraordinary sophistication and accuracy. The question of whether the Antikythera mechanism influenced the development of later astronomical instruments, either directly or through a chain of transmission that has not been fully identified, is one that continues to be investigated. The most likely channel of transmission is through the Byzantine Empire, which preserved much of the Greek scientific and mathematical tradition, and which transmitted it to the Islamic world and eventually to medieval Europe. The Byzantine engineers and astronomers who maintained the Greek scientific tradition may have had knowledge of devices like the Antikythera mechanism, and this knowledge may have influenced the development of the astronomical instruments that were produced in the Byzantine and the Islamic worlds. The absence of any surviving intermediate devices between the Antikythera mechanism and the earliest medieval clockwork is one of the most frustrating gaps in the history of technology. The gap of over 1,000 years between the mechanism and the first medieval clocks suggests either that the tradition of gear-based computing was completely lost during the transition from the ancient to the medieval world, or that intermediate devices were built, but have not survived in the archaeological record. The second possibility, that intermediate devices were built and lost, is consistent with the general pattern of bronze recycling that explains the absence of the Antikythera mechanism's contemporaries, and it suggests that the gap in the record may be a gap in the evidence rather than a gap in the tradition. The relationship between the Antikythera mechanism and the tradition of astrolabe making deserves additional consideration. The astrolabe, which is a two-dimensional representation of the celestial sphere that can be used to solve a variety of astronomical problems, was developed in the Hellenistic period and was widely used in the Islamic world and in medieval Europe. The astrolabe does not use gears, but it embodies mathematical relationships in its physical design, using the principles of stereographic projection to map the three-dimensional celestial sphere onto a two-dimensional surface. The relationship between the astrolabe and the Antikythera mechanism is one of complementarity rather than direct descent. Both devices represent different approaches to the problem of modeling astronomical phenomena using physical instruments. The astrolabe uses a static, two-dimensional representation that can be manually adjusted, while the mechanism uses a dynamic, gear-driven system that produces continuous output. The coexistence of these two approaches in the Hellenistic period suggests that the ancient astronomers and instrument makers were exploring multiple methods of translating astronomical knowledge into physical form, and that the tradition of astronomical instrument making was broader and more diverse than any single surviving artifact can demonstrate. The tradition of geared calendrical devices in the Byzantine world provides some evidence for the continuation of gear-based computing after the ancient period. A fragment of a geared device from the 6th century of the Common Era, known as the Byzantine sundial calendar, was found in the 19th century and has been identified as a calendrical calculator that used gears to track the relationship between the solar and lunar calendars. This device, while much simpler than the Antikythera mechanism, demonstrates that the use of gears in astronomical and calendrical instruments was not entirely lost during the transition from the ancient to the medieval world, and it provides a possible link between the ancient tradition of gear-based computing and the medieval tradition that produced the mechanical clock. The Islamic tradition of mechanical devices, which flourished from the 9th to the 14th centuries, produced a wide range of sophisticated mechanisms, including automata, water clocks, and astronomical instruments. The great Islamic engineer Al-Jazari, who worked in the late 12th and early 13th centuries, wrote a treatise on mechanical devices that describes automata, water clocks, and other mechanisms of remarkable complexity and ingenuity. Al-Jazari's devices demonstrate a command of mechanical principles, including the use of gears, cams, and linkages, that is consistent with a sophisticated tradition of mechanical engineering. The question of whether this tradition was influenced by the ancient Greek tradition, transmitted through channels that have not been fully identified, remains open. The role of the Antikythera mechanism in inspiring modern scientific and engineering education deserves emphasis. The mechanism has been used as a case study in courses on the history of science, mechanical engineering, astronomy, and archaeology, and it provides a compelling illustration of the interdisciplinary nature of scientific investigation. Students who study the mechanism are exposed to concepts from multiple fields, including gear theory, celestial mechanics, ancient history, epigraphy, and materials science, and the integration of these concepts in the study of a single artifact provides a powerful demonstration of the value of interdisciplinary thinking. The development of computer simulations of the mechanism's operation has provided a new tool for education and for research. Digital models of the mechanism that can be rotated, disassembled, and operated in virtual space allow students and researchers to explore the device's internal workings in ways that are not possible with the original fragments or with physical replicas. These simulations, which are available online and in museum installations, have made the mechanism accessible to a global audience and have contributed to the public understanding of the device and its significance. The broader cultural impact of the Antikythera mechanism extends to its influence on the fields of science fiction and speculative history. The mechanism's existence has inspired writers, filmmakers, and other creative artists to explore the idea that ancient civilizations may have possessed technologies that are more advanced than the historical record suggests. While some of these creative works exaggerate or distort the mechanism's capabilities, the best of them use the device as a starting point for thoughtful exploration of the relationship between technology, civilization, and the passage of time. The question of intellectual property in the ancient world is one that the mechanism raises in an indirect way. In the modern world, significant inventions and innovations are typically protected by patents, copyrights, and other forms of intellectual property that allow their creators to benefit from their work and that provide incentives for further innovation. In the ancient world, no such protections existed, and the knowledge of how to build devices like the Antikythera mechanism was transmitted through personal relationships between masters and apprentices, rather than through published documentation. The loss of these personal relationships through death, displacement, or the disruption of the institutional structures that sustained them was sufficient to cause the loss of the technology itself. The question of whether future archaeological discoveries will reveal additional examples of ancient gear-based computing devices is one that motivates ongoing investigation of ancient shipwrecks and archaeological sites around the Mediterranean. The conditions that preserve the Antikythera mechanism, submersion in seawater in a sealed environment, are conditions that could have preserved other bronze devices at other wreck sites, and the systematic investigation of ancient shipwrecks using modern underwater archaeological techniques may yet produce discoveries that will expand our knowledge of the ancient mechanical tradition. Everything we have discussed so far concerns the specific physical features of the Antikythera mechanism, the specific techniques that have been used to decode it, and the specific astronomical functions that it was designed to perform. These are important matters, and the ongoing research on the mechanism continues to produce results of great scientific and historical significance. But beneath these specifics lies a deeper truth, a truth that concerns not just what the mechanism is, but what it represents, what it tells us about the nature of ancient technology, and what its existence implies about the history of human ingenuity and the fragility of technological traditions. The deeper truth is this: the Antikythera mechanism is proof that the ancient world was capable of feats of engineering that we had previously believed to be impossible before the modern era. The device is not merely an impressive artifact. It is a demonstration of capabilities, mathematical, astronomical, and mechanical, that were not supposed to exist in the ancient world, and that force us to revise our understanding of what the ancients could do. This is not science fiction. This is a physical object, examined by scientists using the most advanced imaging technologies available, analyzed by mathematicians and astronomers who have confirmed its computational capabilities, and reconstructed by engineers who have demonstrated that it works as its builders intended. The Antikythera mechanism is not a legend or a speculation. It is a fact that overturns assumptions that have been held by historians of technology for centuries. Something is wrong with our assumptions about the history of technology. The standard narrative of technological progress presents the history of technology as a story of continuous advancement, from the simple tools of the ancient world to the complex machines of the modern era. This narrative implies that the ancients were technologically primitive, that their tools and their devices were crude by modern standards, and that the sophisticated technologies that we use today are the products of a process of accumulation and refinement that has been ongoing since the beginning of human civilization. The Antikythera mechanism challenges this narrative in the most fundamental way possible. The device demonstrates that the ancient Greeks were capable of building a precision-geared computer that modeled the movements of the celestial bodies with an accuracy that would not be achieved again for over 1,000 years. The device was not a crude approximation of a modern instrument. It was a sophisticated, precision-engineered device that embodied mathematical knowledge of the highest order, and that was manufactured using techniques that imply a mature and well-developed tradition of precision metalworking. The implications of this challenge are profound. If the standard narrative of technological progress is wrong, if the ancients were capable of building devices of a sophistication that we had not imagined, then our understanding of the history of technology must be revised. We must acknowledge that technological capability is not a simple progression from primitive to advanced, but a complex process in which capabilities are developed, maintained, lost, and sometimes reinvented over the course of centuries and millennia. The concept of technological regression, the idea that societies can lose technological capabilities that they once possessed, is one of the most important themes that the Antikythera mechanism illustrates. The tradition of precision mechanical engineering that produced the mechanism was lost during the transition from the ancient to the medieval world, and it was not recovered for over 1,000 years. This loss was not the result of a single catastrophic event. It was the result of a gradual process of decline, in which the institutions that had sustained the tradition, the workshops, the schools, the patronage systems that funded research and development, were progressively dismantled as the political and economic structures of the ancient world collapsed. Let that sink in. The ancient Greeks built a computer 2,000 years ago. The technology that produced it was lost, and it took humanity over 1,000 years to build anything comparable again. The gap between the Antikythera mechanism and the earliest medieval clocks, which are the next known examples of gear-based mechanical computing in the Western world, is a gap of over a millennium, a period during which the ability to build such devices simply did not exist. The knowledge, the skills, the tools, and the institutional support that had made the mechanism possible were all lost, and they had to be rediscovered through independent invention before comparable devices could be built again. The loss of the Antikythera tradition raises broader questions about the relationship between technological capability and civilizational stability. The tradition that produced the mechanism was the product of centuries of accumulated knowledge and skill. It depended on the availability of trained craftsmen who knew how to cut precision gears, on the availability of mathematicians and astronomers who could specify the gear ratios and the mechanical arrangements needed to model astronomical phenomena, on the availability of patrons who were willing to fund the construction of complex and expensive devices, and on the availability of a cultural environment that valued the pursuit of knowledge and the development of technology. When any of these conditions failed, the tradition was at risk, and the eventual failure of all of them, in the general collapse of the Western Roman Empire, resulted in the loss of the tradition itself. The question of what other technologies might have been lost along with the Antikythera tradition is one that cannot be answered with certainty, but that is deeply unsettling. If the ancient Greeks could build a device as sophisticated as the Antikythera mechanism, what other devices might they have built that have not survived? The literary sources describe a variety of mechanical devices that were built in the ancient world, including automata, self-moving machines that performed specific actions, water clocks, water organs, and various other mechanical instruments. The physical evidence for these devices is limited, because the bronze and the other metals from which they were constructed were routinely recycled. But the descriptions in the literary sources suggest a tradition of mechanical engineering that was broader and more diverse than the single surviving example of the Antikythera mechanism can demonstrate. The Antikythera mechanism also challenges our understanding of the relationship between science and technology in the ancient world. Historians have traditionally drawn a sharp distinction between Greek science, which was theoretical and contemplative, and Greek technology, which was practical and utilitarian, arguing that the Greeks were more interested in understanding the world than in building machines. The Antikythera mechanism undermines this distinction because it represents a fusion of theoretical knowledge and practical skill that is characteristic of the modern engineering tradition rather than of the ancient philosophical tradition. The mechanism's builders possessed both the theoretical knowledge of astronomy and mathematics and the practical skills of metalworking and mechanical engineering that were needed to translate knowledge into a functioning machine. The broader cultural significance of the mechanism is worth considering. The device was not merely a tool for astronomical calculation, it was a representation of the cosmos, a physical model that embodied the Greek understanding of the order and the regularity of the celestial motions. The ancient Greeks regarded the cosmos as a rational and orderly system, governed by mathematical laws that could be discovered through observation and reason. The Antikythera mechanisms is a physical expression of this belief, a machine that reproduces the order of the cosmos in miniature, demonstrating through the regular motion of its gears that the universe is a comprehensible system that can be modeled and predicted by the human mind. The existence of the Olympic Games dial on the mechanisms adds a dimension that connects the device to the social and the religious life of the Greek world. The Panhellenic Games were among the most important cultural institutions of ancient Greece, bringing together athletes, spectators, and worshippers from across the Greek world in a celebration of physical excellence, religious devotion, and cultural unity. The inclusion of the game's dial on the mechanism suggests that the device was not intended solely for use by professional astronomers or scientists, but was also designed to serve a broader cultural function, connecting the astronomical cycles of the cosmos to the human cycles of festival and celebration that gave meaning and structure to Greek life. The philosophical implications of the mechanism for the history of ideas are substantial. The device demonstrates that the ancient Greeks not only theorized about the mechanics of the cosmos, but also attempted to build physical models that reproduced those mechanics. This empirical approach to cosmology, in which theoretical models are tested and validated by comparison with physical reality, is one of the defining characteristics of modern science. The existence of the Antikythera mechanisms suggests that this approach was more deeply rooted in the ancient tradition than historians have generally recognized, and that the relationship between ancient Greek thought and modern scientific method is closer and more direct than the standard narrative of the history of science implies. The modern study of the Antikythera mechanism has itself become a case study in the power of interdisciplinary collaboration. The decoding of the mechanism has required the combined efforts of astronomers, mathematicians, engineers, classicists, epigraphers, and computer scientists, working together across the boundaries of their individual disciplines. The success of this collaboration, which has produced a far more complete understanding of the mechanism than any single discipline could have achieved alone, demonstrates the value of integrating different forms of expertise in the investigation of complex problems and provides a model for the kind of interdisciplinary research that is increasingly necessary in the modern scientific world. The concept of the knowledge iceberg is useful for understanding the significance of the Antikythera mechanism. The visible portion of the iceberg, the part that rises above the water's surface, represents what we know: the physical device, its gears, its inscriptions, its astronomical functions. The submerged portion of the iceberg, the vastly larger part that is hidden beneath the surface, represents what we do not know: the full tradition of mechanical engineering that produced the device, the other mechanisms that were built by the same tradition, the workshops and the tools that were used, the training systems that transmitted the necessary skills from one generation to the next, and the institutional infrastructure that supported the entire enterprise. The visible portion of the iceberg is extraordinary in itself. The Antikythera mechanism is the most complex mechanical device known from the ancient world, and its discovery has transformed our understanding of ancient Greek technology. But the submerged portion, the tradition that produced the device, is vastly more significant because it represents a body of knowledge and capability that was developed over centuries, and that was lost when the tradition was extinguished. The mechanism is the evidence that the tradition existed. The tradition itself, with all of its accumulated knowledge and all of its unrealized potential, is gone. The loss of the Antikythera tradition is a specific instance of a broader pattern of technological loss that has characterized the transitions between major civilizations throughout human history. The Egyptians possessed techniques of construction and engineering that enabled them to build the pyramids, techniques that were not maintained by the civilizations that succeeded them. The Romans possessed techniques of road building, aqueduct engineering, and concrete manufacture that were lost during the transition to the medieval period. The Chinese possessed techniques of porcelain manufacture, silk production, and iron casting that were unknown in the rest of the world for centuries. In each case, the loss of the technology was accompanied by the loss of the institutional infrastructure that had sustained it: the workshops, the training systems, the supply chains, and the patronage networks that had made the technology possible. The lesson of the Antikythera mechanism is that technology is not self-sustaining. It requires constant effort to maintain, constant investment to develop, and constant institutional support to survive. The mechanism was built by a civilization that possessed all of these things: trained craftsmen, knowledgeable astronomers, wealthy patrons, and stable institutions that supported scientific and technical work. When these supports were withdrawn, the technology died with them, and the knowledge that had been accumulated over centuries of effort was lost. Let that sink in. The most sophisticated mechanical device of the ancient world was built by a civilization that no longer exists, using knowledge that has been lost, by craftsmen whose names are unknown, in workshops that have been destroyed. The device itself survived only because it sank to the bottom of the sea and was protected from the recycling that would have destroyed it if it had remained on land. The tradition that produced it, a tradition that must have been the work of many people over many generations, is gone. All that remains is this single, corroded, incomplete example, a message in a bottle from a lost civilization, a testament to what they could do, and a warning about how easily it can all be taken away. The Antikythera mechanism also raises important questions about the relationship between scientific knowledge and its practical application. The ancient Greek astronomers possessed a body of astronomical knowledge that was, in many respects, comparable to the astronomical knowledge that was available in Europe in the 15th and 16th centuries. They knew the sizes and the distances of the sun and the moon. They could predict eclipses. They had measured the length of the year to within minutes of the correct value. They had catalogued the positions of hundreds of stars. They had developed mathematical models of the planetary motions that, while not correct in their fundamental assumptions, were capable of predicting the positions of the planets with useful accuracy. The Antikythera mechanism demonstrates that this astronomical knowledge was not merely theoretical. It was applied, translated into a physical device that made the abstract mathematical relationships of astronomy concrete and accessible. The existence of the mechanism suggests that the application of astronomical knowledge to practical problems, including the prediction of eclipses, the maintenance of the calendar, and the tracking of the planetary motions, was an established practice in the ancient world, a practice that produced devices of considerable sophistication, and that was supported by the institutional infrastructure of the Hellenistic scientific establishment. The question of how widely such devices were distributed in the ancient world is one that the surviving evidence cannot answer definitively. The literary sources, as we have seen, describe multiple devices that modelled the celestial motions, and the existence of a mature tradition of precision gear cutting implies that the skills and the tools needed to build such devices were available to multiple craftsmen. But the literary evidence is sparse, and the archaeological evidence is limited to a single example, and the question of whether devices like the Antikythera mechanism were common or rare in the ancient world remains open. The concept of a technological horizon is useful for understanding the significance of the Antikythera mechanism. A technological horizon is the boundary between the technologies that a civilization is capable of producing and the technologies that it is not. The Antikythera mechanism reveals that the technological horizon of the ancient Greeks was far more advanced than we had previously believed, extending into realms of precision mechanical engineering that we had assumed were beyond the capabilities of the ancient world. The discovery of the mechanism has pushed the technological horizon of the ancient world outward, revealing capabilities that were previously invisible and raising the question of how much further the horizon might extend if additional evidence were discovered. The comparison between the Antikythera mechanism and the technological achievements of other ancient civilizations provides additional perspective on the significance of the device. The ancient Egyptians, the Mesopotamians, the Indians, and the Chinese all produced technological innovations of great sophistication, and the question of how the Greek mechanical tradition compares with the technological traditions of these other civilizations is one that has been explored by historians of technology. The Antikythera mechanism, with its precision-cut gears and its mathematical sophistication, represents a type of technology that has no known parallel in any other ancient civilization, though the possibility that similar devices were built in other cultures and that they have not survived cannot be ruled out. The digital reconstruction of the Antikythera mechanism, which has been undertaken by several teams of researchers using computer-aided design and three-dimensional printing, has provided new insights into the device's engineering and has demonstrated the feasibility of the proposed reconstructions. The digital models, which can be assembled, disassembled, and tested in virtual space, allow researchers to evaluate the mechanical viability of proposed gear arrangements, to identify potential problems with the design, and to visualize the operation of the mechanism in ways that are not possible with physical models. The digital reconstructions have also been used to produce three-dimensional printed replicas that can be physically assembled and tested, providing practical confirmation that the proposed mechanisms function as intended. The relationship between the Antikythera mechanism and the development of the mechanical clock, which is one of the most important inventions in the history of technology, deserves deeper examination. The mechanical clock, which was developed in Europe in the late 13th or early 14th century, uses a gear train driven by a falling weight or a coiled spring to mark the passage of time. The clock's gear train converts the continuous motion of the driving mechanism into the intermittent, step-by-step motion of the clock hands, using a device called an escapement that controls the rate at which the gear train advances. The Antikythera mechanism does not use an escapement, and it is not a clock in the modern sense. It does not mark the passage of time automatically. Instead, it is driven by a hand-operated input shaft that is turned by the user, but the mechanism's use of a gear train to convert input motion into a variety of output motions that model astronomical phenomena is conceptually similar to the clock's use of a gear train to convert the motion of a weight or a spring into the regular, measurable motion of the clock hands. Both devices use gears to perform a type of computation, converting one form of motion into another according to precise mathematical relationships. The question of whether the mechanical clock was influenced by the ancient tradition of gear-based astronomical modeling, either directly or indirectly, is one that has been debated by historians of technology. The medieval European clockmakers who developed the first mechanical clocks were almost certainly unaware of the Antikythera mechanism, which was lost on the seafloor and would not be discovered for another 500 years. But they may have been aware of other examples of gear-based astronomical instruments, including the astrolabe and the calendrical devices that were developed in the Islamic world, and that may have been transmitted to Europe through the channels of technological exchange that connected the Islamic and the Christian worlds. The evolution of the mechanical clock from a simple timekeeping device to a complex astronomical instrument provides an instructive parallel to the Antikythera mechanisms. The great astronomical clocks that were built in European cathedrals in the 14th and 15th centuries, such as the astronomical clocks at Strasbourg, Prague, and Lund, included displays that showed the positions of the sun, the moon, and the planets, the phases of the moon, the dates of Easter and other movable feasts, and a variety of other astronomical and calendrical information. These clocks, which are among the most complex mechanical devices of the medieval period, represent the culmination of a tradition of astronomical clockmaking that developed over the course of several centuries and that produced devices of increasing complexity and sophistication. The parallel between the Antikythera mechanism and the medieval astronomical clocks is striking, not only in their shared use of gear-based computing to model astronomical phenomena, but also in their cultural significance. Both the mechanism and the medieval clocks were objects of cultural prestige, valued not only for their practical functions, but also for their symbolic significance as representations of the cosmic order. Both were products of intellectual traditions that valued the systematic study of the heavens and the translation of astronomical knowledge into physical form, and both demonstrate the human desire to build machines that reproduce the order of the cosmos, to create physical models that make the invisible visible and the incomprehensible comprehensible. The relationship between the Antikythera mechanism and the modern computer is more distant but no less instructive. The modern digital computer which processes information in the form of binary digits using electronic circuits, is fundamentally different in its technology from the ancient analog computer, which processed information in the form of angular displacements using mechanical gears. But the underlying concept is the same. Both devices use physical systems to perform computations, to model mathematical relationships, and to produce output that represents the results of those computations. The Antikythera mechanism and the modern computer are both machines that think, in the sense that they process information and produce results that embody mathematical reasoning. The ongoing development of new reconstruction proposals for the Antikythera mechanism reflects the continuing vitality of the research and the continuing potential for new discoveries. The reconstruction proposed by Tony Freeth in 2021, which uses a system of concentric ring gears to model the planetary motions, represents the most ambitious attempt to date to reconstruct the complete front display of the mechanism. The proposal has been evaluated by other researchers, some of whom have accepted its general approach while questioning specific details, and others of whom have proposed alternative reconstructions that use different mechanical arrangements to achieve the same astronomical outputs. The debate over the correct reconstruction of the planetary display is one that may not be resolved until additional physical evidence is recovered, either from the original wreck site or from other sources. The surviving fragments of the mechanism do not contain enough information to determine definitively how the planetary motions were modelled, and the reconstruction proposals are based on a combination of the surviving physical evidence, the information provided by the inscriptions, and the general principles of Hellenistic astronomical modelling. The debate is productive, however, because it pushes researchers to develop new and more refined analyses of the evidence, and it highlights the areas where additional information is most needed. The potential for future discoveries that would advance the study of the Antikythera mechanism is considerable. The wreck site itself has not been fully excavated, and the possibility that additional fragments of the mechanism remain on the sea floor is one that continues to motivate underwater archaeological investigation. The development of new imaging technologies, such as neutron tomography and synchrotron radiation imaging, offers the possibility of revealing features of the mechanism that are invisible to the X-ray CT scanning that has been used to date. That the discovery of other ancient mechanical devices, whether from shipwrecks or from land-based archaeological sites, would provide comparative evidence that could illuminate the tradition that produced the Antikythera mechanism and could help to resolve the outstanding questions about the device's design and function. The study of the Antikythera mechanism is one of the great ongoing scientific investigations of our time, and the story of its discovery, its decoding, and its significance is a story that is far from finished. Each new advance in technology, each new analysis of the evidence, each new reconstruction proposal brings us closer to a full understanding of this extraordinary device, and each new discovery reminds us that the ancient world was far more capable, far more sophisticated, far more inventive, and far more creative than we had imagined, and that the full scope of ancient achievement is still being revealed. The Antikythera mechanism is a challenge to our assumptions, a stimulus to our curiosity, and a testament to the enduring power of the human desire to understand the cosmos and to build machines that model its workings. The Antikythera mechanism also speaks to the question of what we mean by technology and how we measure technological achievement. In the modern world, we tend to equate technology with electronic devices, with computers and smartphones and satellites and nuclear reactors. We tend to measure technological achievement by the standards of our own era, judging past civilizations by their proximity to or their distance from the technologies that we consider important. The Antikythera mechanism challenges this perspective by demonstrating that technological achievement can take forms that are very different from the forms that we are accustomed to, and that the ingenuity and the sophistication of a technological tradition cannot be measured by comparing it to our own. The mechanism is a mechanical device built from bronze gears and hand-engraved inscriptions. By the standards of modern technology, it is crude. No electronics, no digital processing, no software, no display screen. But by the standards of its own time, it was a marvel, a device that embodied the highest achievements of Greek mathematics, astronomy, and mechanical engineering in a single portable instrument. The mechanism was not crude, it was different, and the difference between its technology and ours is not a measure of inferiority, but a measure of the diversity of the human technological imagination. The mechanism reminds us that technology is not a destination but a process, not a fixed point but a moving one. The technologies that we consider advanced today will be primitive by the standards of the future, just as the technologies of the ancient world are primitive by the standards of today. But the human impulse that drives technological innovation, the desire to understand the world and to build machines that model its workings, is constant, and it connects us to the builders of the Antikythera mechanism across the vast distance of 2,000 years. The question of how the mechanism was used in practice is one that the inscriptions have helped to answer. The inscriptions describe the device's functions in terms that suggest a practical, hands-on use, with the user turning the input handle to advance the mechanism to a desired date, and then reading the positions of the celestial bodies and the calendar information from the dials. The inscriptions include instructions that describe how to interpret the dial readings and how to use the eclipse predictions, suggesting that the mechanism was intended to be operated by a user who was educated, but not necessarily a professional astronomer. The practical experience of using a working replica of the mechanism, which is described by several of the researchers who have built replicas, provides insight into the device's operation. The replicas demonstrate that the mechanism is relatively easy to operate, with a smooth and steady feel to the input handle and a clear and readable display of the astronomical and calendrical information. The experience of operating a replica also reveals features of the mechanism's design that are not apparent from the study of the fragments alone, including the precision with which the gears mesh, the smoothness with which the pointers advance, and the clarity with which the dial markings can be read. The question of how the mechanism was calibrated, how the pointers were set to the correct positions when the device was first put into operation, is one that has been addressed by several researchers. The calibration of the mechanism would have required the user to set the pointers to positions that corresponded to the known positions of the celestial bodies on a specific date, and then to advance the mechanism forward or backward in time to verify that the predictions were accurate. The calibration process would have been a skilled operation that required knowledge of the current positions of the Sun, the Moon, and the planets, as well as an understanding of the mechanism's internal workings. What does the Antikythera mechanism mean for our understanding of the history of human technology, the nature of scientific progress, and the relationship between the ancient and the modern worlds? The first implication is a humbling recognition that our understanding of the ancient world is incomplete. The discovery of the Antikythera mechanism, which revealed a level of technological sophistication that was entirely unsuspected before its recovery, reminds us that the surviving record of the ancient world is only a fraction of what once existed. The literary sources that describe ancient technology are fragmentary and often vague, and the archaeological record is biased toward objects that survive well in the ground, such as pottery, stone, and some metals. Objects made of wood, leather, textile, and other organic materials, which may have included technological devices of considerable sophistication, have largely disappeared, and the bronze objects that constituted some of the most sophisticated technological products of the ancient world were routinely recycled, destroying the evidence of their existence. The second implication is a recognition that technological progress is not a simple or a linear process. The history of the Antikythera mechanism demonstrates that technologies can be developed, refined, used, and then lost, sometimes for centuries or millennia, before being reinvented by later civilizations. The standard narrative of technological progress, which presents the history of technology as a continuous advancement from primitive to sophisticated, is contradicted by the evidence of the mechanism, which shows that the ancient world achieved a level of sophistication that was subsequently lost. and that was not recovered for over 1,000 years. There is a pause worth taking here. Consider the craftsman, or the team of craftsmen, who built the Antikythera mechanism. Consider the years of training, the depth of knowledge, and the level of skill that were required to design and to construct a device of this complexity. Consider the institutional support, the workshops, the tools, the funding that made the work possible. And consider that all of this, the training, the knowledge, the skill, the institutions, was lost in the centuries that followed, destroyed not by a single catastrophic event, but by the slow, grinding process of civilizational decline that eroded the foundations of the ancient world. The third implication is a challenge to the assumption that the modern world has a monopoly on technological innovation. The Antikythera mechanism demonstrates that the ancient world was capable of feats of engineering that are impressive by any standard, ancient or modern. The precision of the mechanism's gears, the sophistication of its mathematical design, and the ambition of its astronomical modeling are achievements that command respect and admiration, regardless of the era in which they were produced. The mechanism is a reminder that human ingenuity is not a modern invention but a human constant, a capacity that has been expressed in different ways by different civilizations at different times throughout history. The preservation of technological knowledge is not merely a matter of maintaining physical artifacts. It is a matter of maintaining the human institutions, the workshops, the schools, the research centers, the systems of patronage and funding that produce and sustain technological innovation. The Antikythera mechanism was built by people who worked within institutions that supported their work. When those institutions failed, the technology they had produced was lost. The lesson for the modern world is clear. Technological capability depends on institutional support, and the loss of that support can result in the loss of the capability itself. The Antikythera mechanism also raises questions about what other surprises the ancient world may hold. The mechanism was discovered by accident, recovered from a shipwreck that was found by sponge divers who were not looking for archaeological artifacts. The discovery was not the result of a systematic search, but of a fortunate coincidence, and the subsequent understanding of the device was delayed for decades by the limitations of the available technology. If a device of this sophistication could be hidden for 2,000 years, what other devices might be waiting to be discovered in the unexcavated sites and the unexplored waters of the ancient world? The sea floor of the Mediterranean, which was one of the most heavily trafficked waterways in the ancient world, is littered with shipwrecks that have never been fully explored. The underwater archaeological techniques that have been developed in recent decades have made it possible to locate and to investigate these wrecks with a precision and a thoroughness that were not possible in the past. The discovery of additional fragments of the Antikythera mechanism or of other mechanical devices of similar sophistication is a possibility that cannot be ruled out, and the ongoing archaeological investigation of the Mediterranean seafloor may yet produce discoveries that will further transform our understanding of ancient technology. The responsibility to preserve our understanding of the mechanism and to continue the research that is needed to complete the reconstruction of the device falls on the current generation of scientists and scholars. The work of decoding the mechanism is not finished. The planetary display, the most complex and the most poorly preserved portion of the device, has not been definitively reconstructed, and the debate over the specific gear arrangements that were used to model planetary motion continues. The resolution of this debate will require further study of the surviving fragments, possibly supplemented by the discovery of additional fragments from the wreck site, and it will require the continued collaboration of the international team of researchers who have devoted their careers to the study of this extraordinary device. The fourth implication of the Antikythera mechanism is a recognition of the importance of underwater archaeology for the recovery of ancient technology. The mechanism survived because it was lost at sea, where it was protected from the recycling and the destruction that claimed other devices of similar complexity. The seafloor of the Mediterranean is littered with shipwrecks from the ancient world, and many of these wrecks have never been systematically investigated. The possibility that additional mechanical devices, whether similar to the Antikythera mechanism or representing entirely different types of technology, may be preserved in these wrecks is one that justifies continued investment in underwater archaeological research. The development of underwater archaeological techniques has advanced dramatically since the original recovery of the Antikythera mechanism in 1900 and 1901. Modern underwater archaeology uses sophisticated diving technology, including rebreather systems, robotic underwater vehicles, and remotely operated cameras to investigate sites at depths and in conditions that were inaccessible to the sponge divers who found the Antikythera wreck. The application of these modern techniques to the ancient shipwrecks of the Mediterranean has already produced important discoveries, and the potential for future discoveries is enormous. The preservation of the Antikythera mechanism itself is a responsibility that falls on the National Archaeological Museum in Athens and on the international scholarly community. The fragments of the mechanism are irreplaceable, and their continued deterioration, however slow, represents a gradual loss of the information they contain. The ongoing conservation work, combined with the digital documentation that has been produced through CT scanning and other imaging techniques, ensures that the information encoded in the fragments will be available to future researchers, even if the physical objects themselves deteriorate further. But the preservation of the physical fragments remains a priority, because they may contain information that has not yet been detected by current imaging technologies, and that may be revealed by future techniques that are yet to be developed. The responsibility to continue the research extends beyond the preservation of the fragments to the continuation of the intellectual work of decoding the mechanism. The reconstruction of the planetary display, the identification of the mechanism's place of origin, and the elucidation of its cultural context are all ongoing research projects that require the sustained effort of the international team of researchers who have devoted their careers to the study of this extraordinary device. The collaboration between astronomers, mathematicians, engineers, classicists, and archaeologists that has characterized the Antikythera mechanism research project is a model for the kind of interdisciplinary cooperation that is necessary for the investigation of complex artifacts from the ancient world. The Antikythera mechanism reminds us that the past contains surprises that we cannot predict, and that the recovery of ancient knowledge is an ongoing process that may produce transformative discoveries at any time. The mechanism was an unexpected discovery that overturned long-held assumptions about the technological capabilities of the ancient world. The possibility that similar discoveries may be made in the future through the investigation of other shipwrecks, the excavation of other archaeological sites, or the re-examination of objects that have been stored in museum collections without being fully studied is one that should motivate continued investment in archaeological research and in the study of the material culture of the ancient world. The fifth implication of the Antikythera mechanism is a recognition of the value of patience in scientific research. The mechanism was discovered in 1900 and 1901, but its true significance was not understood until the work of Derek de Solla Price in the 1950s and 60s, and the most important advances in the decoding of the device have occurred only in the 21st century. More than 100 years after the initial discovery, the study of the mechanism has required the development of new technologies, including X-ray computed tomography and polynomial texture mapping, that did not exist when the device was first recovered. Each generation of researchers has been able to see features of the mechanism that were invisible to the previous generation, and the process of discovery is still ongoing. This long arc of discovery reminds us that the significance of an archaeological find may not be immediately apparent, and that the full understanding of a complex artifact may require decades or centuries of study and the development of technologies that do not yet exist. The patience to pursue a problem over the course of a lifetime, and the institutional continuity to sustain a research program over the course of multiple lifetimes are essential for the investigation of complex artifacts like the Antikythera mechanism. The scholars who have devoted their careers to the study of the mechanism have demonstrated these qualities in abundance, and their work serves as an example and an inspiration for future generations of researchers. The ethical dimensions of the study of the Antikythera mechanism are worth considering. The mechanism is a Greek artifact recovered from a shipwreck in Greek waters, and it is housed in a Greek museum. The study of the mechanism has been conducted by an international team of researchers, and the results of their research have been published in international scientific journals. The collaboration between the Greek authorities, who are responsible for the preservation of the mechanisms, and the international researchers who have studied it, has been productive and mutually beneficial, but it has also raised questions about the ownership of cultural heritage, the rights of host countries to control access to their archaeological treasures, and the responsibilities of international researchers to share the results of their work with the host country and with the broader public. The mechanism has also raised questions about the presentation of ancient technology in museums and in popular culture. The display of the mechanism in the National Archaeological Museum in Athens, which includes the original fragments alongside explanatory models and multimedia presentations, has been praised for its accessibility and its educational value. But the question of how to present an object as complex and as scientifically significant as the Antikythera mechanism to a general audience, without oversimplifying its significance or overcomplicating its technical details, is a challenge that museum professionals and science communicators continue to address. The sixth implication of the Antikythera mechanism is a recognition that the study of ancient technology has the potential to inspire new approaches to modern engineering. The mechanism's solutions to the problems of modeling complex astronomical phenomena using simple mechanical components demonstrate a level of engineering creativity that is relevant to modern challenges in areas such as miniaturization, low-power computing, and the design of mechanical systems for use in environments where electronic devices cannot function. The study of ancient engineering solutions, including the pin and slot mechanism and the spiral dial arrangement, may suggest new approaches to modern problems that have not been considered by engineers who are trained exclusively in the modern tradition and who may not be aware of the solutions that were developed by their ancient predecessors. The mechanism also reminds us that the boundaries between scientific disciplines are artificial constructs that can impede the kind of integrated, holistic thinking that is necessary for the creation of truly innovative technologies. The fragments of the Antikythera mechanism are housed in the National Archaeological Museum in Athens, displayed in a climate-controlled case that protects the corroded bronze from further deterioration. The fragments are small and unimpressive to the casual viewer, lumps of greenish-brown metal that bear little resemblance to the precision-engineered device that they once constituted. The marine encrustations that covered the mechanism when it was recovered from the seafloor have been carefully removed, revealing the outlines of gear wheels, the traces of inscriptions, and the remains of the shafts and bearings that once held the mechanism together. But beneath the corroded surfaces, the gears still tell their story. The teeth that were cut into the bronze 2,000 years ago still mesh with their neighbours, still embodying the mathematical ratios that model the movements of the sun, the moon, and the planets. The inscriptions that were engraved on the surfaces of the mechanisms still describe the device's functions, still providing instructions for a user who will never come. The mechanism is silent now, its gears frozen in the positions they held when the salt water stopped their motion 2 millennia ago. But the knowledge that it embodies, the astronomical understanding, the mathematical precision, the mechanical ingenuity that went into its design and construction is still legible to those who have the skill and the patience to read it. The Antikythera mechanism is more than an artifact. It is a message from the ancient world, a message that tells us that the people who lived 2,000 years ago were not the technologically primitive beings that we sometimes imagine them to have been. They were skilled, knowledgeable, and ambitious, capable of imagining the cosmos as a comprehensible system, and of building a machine that reproduced that system in miniature. They possessed mathematical knowledge of the highest order, astronomical observations of extraordinary precision, and engineering skills that enabled them to translate their knowledge into a functioning device. They were, in short, our equals in intellect and in ambition, separated from us, not by ability, but by the specific circumstances of history that determined what technologies they developed and what technologies they lost. The loss of the tradition that produced the Antikythera mechanism is a warning. It tells us that technological knowledge is not permanent, that the achievements of one era can be lost in the next, and that the institutions and the traditions that sustain technological innovation require constant effort and constant support to maintain. The ancient Greeks built a computer. That technology was lost. It took humanity 1,000 years to build another one. The gap between the ancient achievement and the medieval recovery is a measure of what can be lost when civilizations decline, when institutions fail, and when the fragile chain of transmission that connects one generation to the next is broken. The mechanism sits in its case in Athens, corroded and silent, a ghost of the device it once was. But the questions it raises are not silent. They echo through the centuries, through the laboratories and the workshops of the modern world, through the imaginations of the scientists and the engineers who study it. What else could they build? What else has been lost? What might we find if we looked more carefully at the sea floor, at the archaeological sites, at the fragments of ancient technology that have been catalogued and stored in museum basements around the world without being fully examined? The Antikythera mechanism was underwater for 2,000 years. It was recovered by accident, studied by pioneers, decoded by teams of scientists, using technologies that did not exist when the mechanism was first recovered. Each generation of researchers has revealed features that the previous generation could not see, and each new discovery has deepened our appreciation of the mechanism's sophistication and our understanding of the civilization that produced it. The process of discovery is not over. It may never be over, because the mechanism, like the cosmos it was designed to model, contains more than we can see at first glance, and its secrets are revealed slowly, one gear at a time, one inscription at a time, one fragment at a time. The gears are still. The bronze is green with age. The sea has given up its treasure, and the world is richer for it, richer in knowledge, richer in understanding, and richer in the humbling recognition that the people who came before us were greater than we knew. The Antikythera mechanism is proof that the past is not what we thought it was, and the past, like the mechanism itself, is still being decoded. The mechanism's gears embody a vision of the cosmos that is both ancient and eternal. The celestial bodies move according to mathematical laws. Those laws can be discovered through observation and reason, and those laws can be translated into physical form, embodied in bronze gears that reproduce the motions of the heavens in miniature. This vision, which was first articulated by the Greek astronomers and philosophers, remains the foundation of modern science, and the Antikythera mechanism is its earliest known physical expression. The mechanism is also a monument to the anonymous craftsmen who built it. Their names are unknown, their workshop has not been found. Their training and their techniques must be inferred from the physical evidence of the device itself. But their skill is undeniable. The precision of their gears, the elegance of their mechanical solutions, and the ambition of their design all testify to a level of craftsmanship that commands admiration and respect across the centuries. They built a machine that has survived for 2,000 years, that has challenged the assumptions of modern historians, and that has inspired scientists and engineers around the world. Their achievement deserves to be remembered, even if their names cannot be. The device is a reminder that the human mind has always been capable of extraordinary things. 2,000 years ago, in a workshop that may have overlooked the blue waters of the Mediterranean, a craftsman sat down with bronze and tools and mathematical tables and set about building a model of the universe. The universe he modelled was the geocentric cosmos of the ancient Greeks, a cosmos that we now know to be incorrect in its fundamental structure. But the impulse that drove him, the desire to understand, to model, to predict, to make the invisible visible and the incomprehensible comprehensible. That impulse is the same impulse that drives science and engineering today. The Antikythera mechanism is proof that this impulse is as old as civilization itself. The Antikythera mechanism was built by human hands, designed by a human mind, and lost through human carelessness or misfortune. It was recovered by human effort, studied by human ingenuity, and decoded by human persistence. The device is a testament to the capabilities of the human species, a demonstration that the desire to understand the world and to build machines that model its workings is not a modern invention but a human constant, expressed in different forms by different civilizations at different times throughout history. The fragments in the museum case in Athens are small and dark and corroded. They do not look like much, but they contain, within their corroded surfaces, the evidence of one of the most extraordinary achievements in the history of human technology. They contain the gears that modelled the cosmos, the inscriptions that described the heavens, and the mechanical ingenuity that translated mathematical knowledge into physical motion. They contain the proof that the ancient world was not what we thought it was, and the promise that the past still has the power to surprise us. The mechanism waits in its case, patient and silent, its gears frozen, its story still being told. And somewhere beneath the waves of the Mediterranean, on a sea floor littered with the debris of ancient commerce and ancient ambition, there may be other mechanisms, other devices, other products of the same tradition that produced the Antikythera mechanism. The sea has not yet given up all of its secrets. The past has not yet been fully decoded, and the story of the Antikythera mechanism, the world's oldest known computer, is a story that is still being written, one discovery at a time, one gear at a time, one truth at a time. The corroded gears in the Athens Museum case are a message from across the centuries, a message that says, "We were here, we understood, we could do this." The message is directed not at scholars or at engineers or at any specific audience. It is directed at the future, at anyone who would listen, at anyone who would take the trouble to decode the corroded bronze and to hear what it has to say. The message has been waiting for 2,000 years, and now, finally, we are beginning to hear it. The Antikythera mechanism is proof that the human desire to understand the cosmos is as old as civilization. It is proof that the translation of understanding into physical form, the building of machines that model the workings of the universe, is not a modern invention but an ancient practice, and it is proof that the achievements of the past, no matter how distant, no matter how obscured by the passage of time, can still speak to us, can still teach us, and can still remind us of the extraordinary capabilities of the human mind.